The event horizon of a black hole. The event horizon marks the point of no return, the boundary where escape velocity equals the speed of light, and nothing, not even light itself, can break free from a black hole's gravitational grip. For Sagittarius A-star, the supermassive black hole lurking at the Milky Way center with a mass 4 million times the Sun's, the event horizon stretches 24 million kilometers across roughly 60 times the distance between Earth and Sunday. Crossing this boundary means entering a region of spacetime so warped that all paths lead inward. Time itself behaves strangely near the horizon. An observer falling toward a black hole would see the outside universe accelerate into the future, watching stars die and galaxies evolve in fast forward. Meanwhile, a distant observer watching the infalling person would see them slow down asymptotically, never quite crossing the horizon, frozen in time by extreme gravitational time dilation. The person falling experiences no barrier. They cross smoothly, but once across, return becomes impossible. Gargantua, the fictional supermassive black hole from the film Interstellar, based on calculations by physicist Kip Thorne, demonstrates extreme time dilation effects. Near Gargantua's event horizon, time dilation reaches the point where 1 hour on a planet orbiting just outside the horizon equals 7 years on Earth, a time dilation factor of roughly 61,000. This isn't fiction. General relativity predicts such effects for rapidly rotating black holes, with spin approaching the maximum theoretical limit. The mathematics describing this are encoded in the Kerr metric, the solution to Einstein's equations for rotating black holes, discovered by Roy Kerr in 1963. Real supermassive black holes likely spin rapidly, having formed through accretion and mergers that preferentially add angular momentum. M87 star, the black hole imaged by the Event Horizon Telescope in 2019, rotates at significant fractions of maximum spin based on jet properties and accretion disk modeling. Spaghettification, the horrifying process of being stretched vertically while compressed horizontally, results from tidal forces that become extreme near black hole horizons. Tidal forces arise from the difference in gravitational pull across an object. Your feet, closer to the black hole, experience stronger gravity than your head. For stellar mass black holes with masses around 10 solar masses and event horizons only 30 kilometers across, tidal forces at the horizon exceed 10 to the 12th times Earth's surface gravity, 1 trillion times stronger. A human approaching such a horizon would be torn apart long before crossing, stretched into a stream of atoms. But supermassive black holes are different. Their enormous event horizons mean gentler tidal gradients. At Sagittarius A-star's horizon, tidal forces are only a few Earth gravities, uncomfortable but not immediately fatal. An astronaut could cross the horizon intact, experiencing increasing tidal forces only deeper inside as they approach the singularity. The information paradox haunts black hole physics, posing a fundamental conflict between quantum mechanics and general relativity. Quantum mechanics insists information cannot be destroyed, knowing a system's complete quantum state allows predicting its future and reconstructing its past. But black holes seem to violate this principle. When matter falls past the event horizon, all information about its quantum state, its precise configuration of particles, fields, and quantum numbers appears lost forever, hidden behind the horizon where no signal can escape. Stephen Hawking's discovery in 1974 that black holes emit thermal radiation, now called Hawking radiation, made the paradox worse. Hawking radiation carries no information about what fell in. It's perfectly thermal, determined solely by the black hole's mass, spin, and charge. As black holes evaporate through Hawking radiation over incomprehensibly long timescales, the information seemingly vanishes completely, destroyed. The firewall hypothesis, proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, suggests the event horizon might not be the smooth, uneventful surface general relativity predicts. To resolve the information paradox while preserving quantum mechanics, the hypothesis proposes that violent quantum effects create a firewall, a region of enormous energy density at or near the horizon. Any object crossing would be incinerated instantly by energies exceeding anything imaginable, vaporized into radiation before experiencing the interior. This contradicts the equivalence principle, Einstein's insight that freely falling observers shouldn't detect anything special at the horizon. The firewall paradox remains unresolved, with physicists divided on whether firewalls exist, whether information is somehow preserved in Hawking radiation through subtle correlations, or whether entirely new physics beyond general relativity and quantum field theory is needed. Hawking radiation ensures even black holes are mortal, evaporating over timescales vastly exceeding the current universe's age. The mechanism involves quantum fluctuations near the event horizon. Empty space constantly produces particle-antiparticle pairs that normally annihilate immediately. Near a horizon, one particle can fall in while its partner escapes, appearing as radiation to distant observers. The black hole loses mass equivalent to the escaped particle's energy. The evaporation rate depends on mass smaller black holes radiate faster. A stellar mass black hole of 10 solar masses evaporates in roughly 10 to the 67th years. Supermassive black holes, like Sagittarius A-star, take 10 to the 98th years. Microscopic black holes, if they could form, would explode in nanoseconds. As black holes shrink, temperature increases inversely with mass, accelerating evaporation. The final moments see the black hole becoming microscopically small and extraordinarily hot, detonating in a burst of gamma rays. The nearest known stellar mass black hole to Earth is Gaia BH1, discovered in 2022 through analysis of Gaia Space Telescope astrometry data. Located 1,560 light-years away in the constellation Ophiuchus, Gaia BH1 has a mass approximately 10 solar masses and orbits a Sun-like star with a 185-day period. The black hole was identified through the star's wobble periodic position shifts, caused by orbiting an unseen massive companion. This discovery is significant because Gaia BH1 is dormant, not actively accreting matter, and producing X-rays, making it undetectable by traditional X-ray surveys. The finding suggests many stellar mass black holes lurk nearby, invisible except through gravitational effects. Estimates predict roughly 100 million stellar mass black holes populate the Milky Way, formed from massive star deaths over the galaxy's 1-3 billion year history. Most are solitary wanderers in interstellar space, detectable only if they accrete gas or orbit visible companions. Approaching a black hole's event horizon reveals the universe's ultimate horror, a place where time stops, space becomes inescapable, and the laws of physics as we understand them break down. The horizon represents a one-way membrane in spacetime geometry. Light emitted just outside can escape, redshifted to lower energies by gravitational effects. Light emitted just inside cannot escape at all. It's trapped, destined to fall inward regardless of direction. This asymmetry creates the black hole's defining characteristic, perfect blackness. No light escapes, so black holes are invisible except through their gravitational effects on surrounding matter and space-time. The Event Horizon Telescope's 2019 image of M87 star didn't actually image the horizon itself. It imaged the photon ring, light emitted by hot gas just outside the horizon, gravitationally lensed by the black hole's extreme warping of spacetime into a bright ring surrounding the shadow. The surface area of a black hole's event horizon encodes entropy, a measure of hidden information according to the holographic principle and black hole thermodynamics developed by Jacob Bekenstein and Stephen Hawking. A black hole's entropy equals 1/4 of its horizon area, measured in Planck units, fundamental quantum units of area, approximately 10 to the minus 70th square meters. For Sagittarius A-star, this entropy exceeds 10 to the 91st, vastly larger than the entropy of all matter and radiation that formed it. This suggests black holes are the most efficient information storage devices in the universe, encoding information on their surfaces rather than in their volumes. The holographic principle extends this idea, proposing that all information in any volume of space can be encoded on its boundary surface. Black hole horizons are the ultimate realization of this principle, storing every bit of information about everything that ever fell in, though in a form completely inaccessible to outside observers. Inside a black hole beyond the horizon. Beyond the event horizon, spacetime's structure inverts in a way that defies intuition. Time becomes a spatial direction pointing toward the singularity, while one spatial direction becomes time-like, pointing inevitably into the future. In normal spacetime, you can move freely in space, but are dragged forward in time. Inside a black hole, the singularity lies in your future the same way tomorrow does. You cannot avoid reaching it any more than you can avoid tomorrow's arrival. All paths lead to the singularity regardless of what you do. Firing rockets at maximum thrust only changes when you hit the singularity, not whether. Turning around and thrusting back toward the horizon is futile. You're moving through time toward the singularity, and time's arrow permits no reversal. This isn't because gravity is so strong, it's because space-time geometry has changed fundamentally. The singularity is not a place in space, but a moment in time, your final moment. The singularity represents the point where general relativity's equations break down, predicting infinite curvature, infinite density, and zero-volume physical impossibilities, signaling that the theory reaches its limits. In a non-rotating Schwarzschild black hole, the singularity is a point at the center where all infalling matter crushes to infinite density. In a rotating Kerr black hole, the singularity becomes a ring, a circle, where rotation prevents all mass from collapsing to a point. The ring's singularity has radius proportional to the black hole's angular momentum, ranging from 0 for non-rotating holes to the maximum possible for extremal Kerr black holes spinning at the theoretical limit. Neither singularity type is thought to exist as described quantum gravity effects, unknown in our current theories, should prevent true infinities. The singularity might be replaced by a Planck scale structure with enormous but finite density, or spacetime might quantum tunnel to another region, or entirely new physics intervenes. The Cauchy horizon appears in rotating black hole solutions, forming an inner boundary beyond which predictability fails. Spacetime becomes causally disconnected, and laws of physics as we know them cannot determine outcomes. Between the outer event horizon and Cauchy horizon lies the ergosphere, a region where frame dragging is so strong that all objects must rotate with the black hole, though escape is still possible. Inside the Cauchy horizon, closed, time-like curves might exist, paths through spacetime that loop back to their own past, creating time travel paradoxes. Roger Penrose and others argued the Cauchy horizon is unstable. Any perturbation in falling matter, gravitational waves, vacuum fluctuations blows up the horizon's energy density to infinity, creating a singularity at the Cauchy horizon that prevents traversing it. This cosmic censorship hypothesis protects causality by ensuring singularities remain hidden behind event horizons, and Cauchy horizons remain inaccessible. Frame dragging, also called the Lentz-Thirring effect, after Joseph Lentz and Hans Thirring, who predicted it in 1918, becomes extreme near rotating black holes. Rotation literally drags spacetime around the black hole like a whirlpool. In the ergosphere, the region between the event horizon and a boundary called the static limit, frame dragging is so intense that remaining stationary is impossible. Even light must orbit in the black hole's rotation direction. An observer trying to hover stationary would need to move faster than light relative to local spacetime, which is impossible. The only option is to orbit, swept along by spacetime's rotation. The Penrose process exploits this. Particles entering the ergosphere can split, with one fragment falling into the hole and the other escaping with more energy than the original particle, extracting rotational energy from the black hole. This mechanism might power astrophysical jets from black holes. The journey time from horizon to singularity depends on black hole mass and the traveler's trajectory. For a stellar mass black hole of 10 solar masses, an observer falling freely from the horizon reaches the singularity in approximately 15 microseconds faster than a human nerve impulse. For Sagittarius A-star's 4 million solar mass black hole, the journey takes about 40 seconds. For the most massive known supermassive black holes exceeding 10 billion solar masses, an infalling observer might survive hours before reaching the singularity, experiencing increasing tidal forces but remaining conscious until the final moments. During this journey, the observer sees strange phenomena. Looking backward toward the horizon shows the outside universe blue-shifted, accelerated into the future, potentially seeing the universe's end compressed into moments. Looking forward shows increasingly red-shifted light from matter that fell in earlier, stretched to longer wavelengths by extreme gravitational effects as space-time curvature intensifies toward the singularity. No observations from inside a black hole are possible. The event horizon acts as a one-way information barrier, preventing any signal from escaping to inform outside observers about interior conditions. Everything known about black hole interiors comes from theoretical calculations, solving Einstein's field equations. General relativity provides exact solutions for idealized black holes, Schwarzschild for non-rotating, uncharged holes, Kerr for rotating, uncharged holes, Reissner, Nordstrom for charged, non-rotating holes, Kerr, Newman for rotating, charged holes. But real astrophysical black holes are more complex. They formed from collapsing stars or merging black holes, processes that leave imprints, gravitational waves, matter distributions, magnetic fields that might affect interior structure. Quantum effects become important at the Planck scale, approximately 10 to the minus 35th meters, where quantum fluctuations of spacetime itself dominate. Near singularities, quantum gravity and unknown theory unifying general relativity and quantum mechanics determines what actually happens. Theoretical explorations suggest exotic possibilities beyond classical general relativity. Some solutions to Einstein's equations allow traversable wormhole shortcuts through space-time connecting distant regions or even different universes. The Kerr solution's maximal extension includes a second exterior region, another universe, connected through the ring singularity. Infalling observers might pass through the ring and emerge in this other universe, rather than being destroyed at a singularity. But classical general relativity allows many solutions that quantum effects or stability analysis rule out. Traversable wormholes require exotic matter with negative energy density, violating energy conditions thought to hold in nature. Wormhole throats are unstable, pinching off before anything can traverse them. Most physicists believe real black holes have genuine singularities regions where spacetime ends and no escape or passage to other universes is possible. The singularity is the ultimate dead end. The maximally extended Kerr solution's Penrose diagram, a conformal map showing the entire spacetime structure, reveals a complex geometry. The diagram shows infinite sequences of universes connected through ring singularities and anti-horizons. An infalling observer could theoretically avoid the singularity by passing through the ring, emerging into another universe, or even the same universe, at a different location or time. But these extended solutions are almost certainly unphysical. They assume the black hole has existed forever and is perfectly isolated. No matter falls in except the observer. Real black holes form from stellar collapse or mergers, processes that modify interior structure. Perturbations from infalling matter destabilize the Cauchy horizon, likely creating a singularity there. The extended regions beyond the Cauchy horizon probably don't exist in nature. The interior of a real black hole is likely far simpler and deadlier, a region of increasingly extreme spacetime curvature, leading inevitably to a singularity where time ends. The surface of a neutron star, PSR J 348 plus 0432, a neutron star located 2,100 light-years away in the constellation Taurus, holds the record for the highest precisely measured mass at 2.01 solar masses, just barely below the theoretical maximum mass, beyond which neutron degeneracy pressure cannot support the star against gravitational collapse to a black hole. This mass is compressed into a sphere roughly 12 kilometers in radius, about the size of Manhattan. The resulting surface gravity is 2 times 10 to the 11th times Earth's surface gravity, 200 billion times stronger. Standing on the surface would be impossible. Any object would be crushed flat instantly, compressed to thicknesses measured in atomic diameters. The escape velocity reaches 64,000 kilometers per second, 21% the speed of light. Light emitted from the surface is gravitationally redshifted, losing roughly 20% of its energy climbing out of the gravitational well. Time runs 20% slower at the surface than in flat spacetime far away, measured by comparing clock rates through general relativistic time dilation. Mountains on neutron stars cannot exceed about 5 millimeters in height before the crust's material strength fails and gravity flattens them. The crust, composed of iron nuclei arranged in a crystalline lattice, immersed in a sea of degenerate electrons, has tensile strength far exceeding any terrestrial material, roughly 10 to the 18th pascals, compared to 10 to the 9th pascals for steel. But even this extraordinary strength cannot support structures against 200 billion G gravity. The maximum mountain height is proportional to the breaking strength divided by density times gravity. For neutron star parameters, this yields millimeters. These tiny mountains matter for astrophysics. Asymmetries in mass distribution create quadrupole moments that emit gravitational waves as the neutron star rotates. The Crab pulsar, spinning 30 times per second, loses rotational energy partly through electromagnetic emission and partly through gravitational wave emission from crustal asymmetries. Observing this spin-down constrains the size of mountains, testing crust strength models. Surface temperatures reach 600,000 to 1 million Kelvin for young neutron stars, making them potent X-ray sources. Neutron stars are born at temperatures exceeding 10 billion Kelvin during core collapse supernovae. Within minutes, neutrino emission cools the interior to 100 million Kelvin. Over thousands of years, photon emission from the surface cools it to millions of Kelvin. The Crab pulsar, only 970 years old, has a surface temperature around 1.6 million Kelvin, detected through thermal X-ray emission. Older neutron stars cool further. Those millions of years old drop below 100,000 Kelvin, entering the optical regime. Eventually, after billions of years, they cool to thousands of Kelvin, becoming invisible except through radio emission from their magnetospheres or accretion if they capture matter. Cooling rate depends on interior composition. Exotic matter like quark cores or pion condensates would cool faster through enhanced neutrino emission, providing observational tests for interior physics. Magnetic fields on neutron stars range from 10 to the 8th Gauss for typical pulsars to 10 to the 15th Gauss for magnetars the strongest magnetic fields known in the universe. For comparison, Earth's magnetic field is 0.5 Gauss. Sunspots have fields around 3,000 Gauss. Laboratory magnets reach 100,000 Gauss in continuous fields, briefly achieving millions of Gauss before destroying themselves. Neutron star fields, quadrillion times stronger, arise from magnetic flux conservation during core collapse. When a star's iron core collapses from 5,000 kilometers radius to 10 kilometers radius, the same magnetic flux compresses into an area 250,000 times smaller, intensifying the field by this factor squared 60 billion times. Fields this strong have bizarre effects. They alter atomic structure, distorting electron orbitals into cigar shapes aligned with the field. They enable exotic photon splitting processes, where single photons split into pairs, violating energy conservation classically, but allowed quantum mechanically in strong fields. The crust consists of iron, 5-6 nuclei, arranged in a body-centered cubic lattice at densities around 10 to the 14th grams per cubic centimeter, 100 trillion times denser than water. As density increases with depth, neutron drip begins at 4 times 10 to the 11th grams per cubic centimeter. Neutrons leak out of nuclei, becoming unbound but trapped in the crust by gravity and pressure. Deeper still, nuclei become increasingly neutron-rich, forming exotic isotopes that cannot exist in normal matter. At the crust core boundary, around 10 to the 14th grams per cubic centimeter, nuclear matter transitions to a neutron superfluid, a quantum liquid where neutrons flow without viscosity. The crust is not solid in the sense of terrestrial rocks. It's a quantum solid where nuclei occupy lattice sites, but quantum zero-point motion prevents them from being truly fixed. The lattice has a shear modulus resistance to deformation billions of times greater than steel, yet it can crack during starquakes when magnetic stress exceeds the breaking strain. Any matter hitting a neutron star's surface undergoes instant and violent transformation. Material falling from rest at infinity reaches the surface at 64,000 kilometers per second, 21% light speed. The kinetic energy per nucleon is roughly 20 MeV, sufficient to overcome nuclear binding energy and disintegrate nuclei into protons and neutrons through spallation. The impact creates an explosion releasing 10 to the 18th ergs per gram, exceeding nuclear weapons by factors of 1,000. Surface temperature spikes to billions of Kelvin locally, triggering explosive nuclear fusion. Hydrogen fuses to helium, helium to carbon, carbon to heavier elements in seconds. Type I X-ray bursts, observed from accreting neutron stars, result from this process. Gas accumulates on the surface until pressure and temperature reach fusion ignition thresholds. The entire accumulated layer, 10 to the 20th to 10 to the 22nd grams, undergoes explosive burning in seconds, releasing 10 to the 39th to 10 to the 42nd ergs and brightening the X-ray flux by factors of 10 to 1,000. Pulsar lighthouse effects create the characteristic pulsed emission that gives pulsars their name. Neutron stars rotate rapidly, periods ranging from milliseconds to seconds due to angular momentum conservation from the progenitor star's core. The magnetic field axis is typically misaligned with the rotation axis by tens of degrees. Charged particles accelerated along magnetic field lines emit beamed radiation radio waves, X-rays, gamma rays, concentrated along the magnetic poles. As the star rotates, these beams sweep across the sky like lighthouse beams. When a beam sweeps across Earth, we detect a pulse. The pulses are extraordinarily regular, more stable than atomic clocks for some pulsars, because rotation period depends only on angular momentum and moment of inertia, both conserved quantities changing only slowly through electromagnetic braking and gravitational wave emission. The fastest known pulsar, PSRJ 1748-2446 AD, rotates 716 times per second, completing a revolution in 1.4 milliseconds. At its equator, the surface moves at 15% light speed, the interior of a neutron star. The outer crust extends from the surface down to densities around 4 times 10 to the 11th grams per cubic centimeter. Where neutron drip begins, the point where nuclei become so neutron-rich that neutrons begin leaking out, no longer bound within individual nuclei. Above neutron drip, the crust resembles a bizarre solid, iron 5-6 nuclei arranged in a crystalline lattice with electrons moving freely through the structure. Below neutron drip, unbound neutrons fill the space between increasingly exotic, neutron-rich nuclei. These nuclei exist nowhere else in the universe. Isotopes like nickel-130 or iron-90 with neutron-to-proton ratios far exceeding stability limits under normal conditions. The free neutrons form a degenerate gas, their quantum states filling up to high energies due to the Pauli exclusion principle, preventing multiple neutrons from occupying the same state. The neutron gas contributes to pressure support, while the nuclear lattice provides structural strength, enabling the crust to sustain mountains and support magnetic field stresses. The inner crust, extending from neutron drip down to the crust core boundary at roughly 10 to the 14th grams per cubic centimeter, contains nuclear pasta, exotic nuclear matter phases, named after pasta shapes they resemble in computer simulations. As density increases, nuclei can no longer maintain spherical shapes. Coulomb repulsion between protons and the neutron gas pressure surrounding them cause nuclei to deform into rods, slabs, tubes, and bubbles. The nuke phase consists of spherical nuclei in a neutron gas. The spaghetti phase has rod-shaped nuclei aligned parallel. The lasagna phase shows slab-like nuclei forming layered structures. Higher densities produce antipasta. Neutron matter with cylindrical holes, the anti-spaghetti or bucatini phase, and spherical bubbles, the anti-gnocchi or Swiss cheese phase. Pasta phases have enormous shear moduli, resisting deformation. They might be the strongest material in the universe, with breaking strains 10 billion times greater than steel. The outer core begins at the crust core boundary, where nuclear matter transitions to a neutron superfluid with a sprinkle of protons forming a proton superconductor. Superfluidity arises when particles form Cooper pairs, bound states analogous to electron pairs, in superconductors that condense into a macroscopic quantum state. Neutrons pair through strong nuclear forces, forming spin triplet pairs. These pairs condense, allowing neutron matter to flow without viscosity, a superfluid where vorticity is quantized and friction vanishes. Protons similarly pair and condense into a superconducting state where electrical resistance disappears. The coexistence of neutron superfluidity and proton superconductivity has profound effects. Magnetic flux penetrates the core in quantized vortex lines, thin filaments carrying 1 quantum of flux each. The core's magnetic field structure consists of billions of flux tubes threading the superconductor, pinned to the neutron superfluid's quantized vortices in a complex coupled system affecting pulsar spin-down and glitches. The inner core, at densities exceeding 2 to 3 times nuclear saturation density, around 5 times 10 to the 14th grams per cubic centimeter, might contain quark matter where neutrons and protons dissolve into their constituent up and down. Quarks. Quantum chromodynamics, the theory of strong interactions, predicts that at sufficiently high densities, quarks become asymptotically free, interacting weakly and moving independently rather than being confined in hadrons. This quark matter might exist in a color-flavor locked phase, where quarks of different colors and flavors pair, forming a color superconductor. Even more exotic, strange quarks, normally unstable and decaying rapidly, might be stable at high densities, forming strange quark matter. The strange matter hypothesis proposes that strange quark matter might be the true ground state of baryonic matter, more stable than atomic nuclei. If true, neutron stars could be strange stars entirely composed of strange quark matter with only a thin nuclear crust. Densities at the core reach 10 to the 15th grams per cubic centimeter, 1 billion tons per cubic centimeter. A teaspoon of this matter weighs 10 billion tons more than all humanity's mass combined. At these densities, matter is compressed beyond nuclear saturation. Nucleons overlap, losing individual identities. The equation of state, the relationship between pressure and density, becomes uncertain. Multiple models exist: the APR equation based on nucleon interactions, the SLI equation including hyperons particles like lambda and sigma containing strange quarks, and various quark matter equations. Different equations predict different maximum neutron star masses. Stiffer equations, allowing higher pressures, support more massive stars. The observed 2.01 solar mass pulsar constrains equations. Any model predicting maximum masses below 2.01 solar masses is ruled out. The stiffest models allow maximum masses around 2.5 solar masses. The Neutron Star Interior Composition Explorer, NISA, mounted on the International Space Station, measures neutron star masses and radii through X-ray timing and spectroscopy. NISA observes X-ray pulsations from rotating neutron stars, analyzing pulse profiles, the brightness variations during rotation. Pulse shape depends on mass, radius, and surface emission pattern. General relativistic effects, gravitational lensing, Doppler beaming, gravitational redshift distort observed pulse profiles in ways dependent on the mass-to-radius ratio. By fitting observed profiles to models, NISA constrains masses and radii simultaneously. Observations of PSRJ 30 plus 0451 yielded a radius of 13 kilometers with mass 1.44 solar masses. PSRJ 740 plus 6,620 has a radius 12 to 14 kilometers with mass 2.08 solar masses. These measurements constrain the equation of state, favoring moderately stiff models and disfavoring very soft equations predicting small radii or very stiff equations predicting large radii. Tidal deformability measurements from the neutron star merger GW 170817, detected by LIGO and Virgo on the 17th of August 2017, provide independent constraints on the equation of state. Tidal deformability describes how much a neutron star deforms under the gravitational tidal forces of its companion during inspiral. Stiffer equations produce less deformable stars. The star's material resists tidal distortion more strongly. Softer equations allow more deformation. Tidal effects imprint measurable corrections to gravitational wave signals during the final seconds before merger. Analysis of GW 170817 found tidal deformabilities, implying neutron star radii around 11 to 13 kilometers for 1.4 solar mass stars, consistent with NISA results. Combining gravitational wave and X-ray constraints tightens limits on the equation of state, excluding the softest and stiffest models and favoring intermediate stiffness with nuclear symmetry energy, a measure of proton-neutron asymmetry effects around 30 to 40 MeV. Hyperons baryons containing strange quarks might appear at densities exceeding twice nuclear saturation. The lambda particle, with composition up-down strange, becomes energetically favorable when chemical potentials for up and down quarks reach the strange quark threshold. Converting neutrons to lambdas reduces energy, so lambdas populate the core. Sigma and Xi hyperons follow at higher densities. Hyperons soften the equation of state. They provide additional degrees of freedom, absorbing energy without contributing as much to pressure, reducing maximum neutron star mass. This creates the hyperon puzzle. Many hyperon equations predict maximum masses around 1.5 solar masses, far below observed 2.01 solar masses. Resolving this puzzle requires either that hyperons don't appear perhaps repulsive, three-body forces suppress them, or that currently unknown repulsive hyperon-hyperon and hyperon-nucleon interactions stiffen the equation sufficiently to support observed masses. A magnetar starquake, SGR 1806-20, a soft gamma repeater located 50,000 light-years away on the opposite side of the Milky Way, hosts the strongest confirmed magnetic field known in the universe at 10 to the 15th Gauss, a quadrillion times Earth's field. On the 27th of December 2004, this magnetar experienced a catastrophic starquake that released 10 to the 46th ergs of energy in 0.2 seconds more energy in 1/5 of a second than the Sun emits in 250,000 years. The gamma ray burst from this event saturated every detector it struck, traveling across the galaxy in 50,000 years and impinging on Earth with enough intensity to ionize Earth's upper atmosphere measurably. The ionization, detected by very low-frequency radio monitoring, caused the nighttime ionosphere to behave like daytime, an unprecedented effect from an event 50,000 light-years away. If SGR 1806-20 were 10 light-years from Earth, the gamma-ray flux would have caused mass extinctions. The gamma-ray flux that reached Earth on the 27th of December 2004 peaked at roughly 1 erg per square centimetre, comparable to receiving in seconds the energy flux from the Sun over an entire day. But as gamma rays, instead of visible light, this flux ionized atoms in Earth's ionosphere, the layer 60 to 1,000 kilometers altitude, where solar ultraviolet normally ionizes gases, creating the D, E, and F layers critical for radio communication. The sudden ionization compressed the ionosphere from nighttime to daytime configuration, affecting very low-frequency radio propagation. VLF signals normally reflect off the ionosphere at altitudes 70 to 90 kilometers at night. The magnetar burst lowered this reflection height to 60 kilometers, changing signal characteristics detectably by VLF monitoring stations. The effect lasted several hours as the ionosphere slowly recombined, returning to normal nighttime configuration. This demonstrated that extrasolar events can affect Earth measurably despite enormous distances. Crust cracking initiates starquakes when magnetic stress exceeds the crust's breaking strain. Magnetar magnetic fields are so intense that magnetic pressure, proportional to field strength squared, generates stresses comparable to the crust's material strength. The magnetic field evolves over centuries through ohmic dissipation, reconnection, and Hall drift processes, rearranging field geometry. As the field evolves, magnetic forces twist and deform the crust. The crust resists elastically up to its breaking strain, roughly 0.1, meaning it can deform by 10% before fracturing. When stress exceeds this limit, the crust cracks suddenly, like earthquake faults on Earth, slipping when tectonic stress exceeds friction. The cracking releases stored elastic energy explosively. Magnetic field lines anchored in the crust snap and reconnect violently, accelerating charged particles to relativistic energies and generating the gamma-ray burst. The quake magnitude, expressed on a scale analogous to Earth's Richter scale, reaches approximately 32, far exceeding anything terrestrial. The Richter scale is logarithmic, with each unit representing a factor of 32 increase in energy. The largest earthquakes in human history, the 1960 Chile earthquake, and 2004 Indian Ocean earthquake reached magnitude 9.5, releasing roughly 10 to the 18th ergs. The magnetar quake at 10 to the 46th ergs is 28 orders of magnitude stronger. Extending the Richter scale, this corresponds to magnitude 32. The quake shifts the entire crust suddenly, changing the neutron star's moment of inertia and angular momentum distribution. This spins up the rotation measurably. The 27th of December 2004 event increased SGR 1806-20's spin frequency by 0.05 Hz. The crust displacement, estimated at roughly 10 meters over the 10-kilometer radius, represents catastrophic structural failure affecting the entire star. X-ray flares following the initial giant outburst continue for years, indicating ongoing crustal settling and magnetic field rearrangement. SGR 1806-20 showed enhanced X-ray emission and sporadic flaring for more than 2 years after the December 2004 event. The quake fractures the crust into multiple plates that slowly relax, generating aftershocks, smaller bursts, releasing residual stress. Magnetic field reconnection events continue as field lines seek lower energy configurations. The crustal fractures create seismic waves oscillations propagating through the neutron star interior. These oscillations modulate X-ray emission periodically at frequencies 18 Hz to 2000 Hz, detected as quasi-periodic oscillations in the burst tail, lasting 400 seconds after the main event. The oscillation frequencies reveal the neutron star's seismic mode's fundamental vibrations dependent on mass, radius, and equation of state, providing rare glimpses into neutron star interiors. SGR 0526-66, another soft gamma repeater in the Large Magellanic Cloud 160,000 light-years away, produced the first recorded magnetar giant flare on the 5th of March 1979. The event resembled the 2004 burst, but was less energetic, releasing roughly 10 to the 44th ergs, still exceeding the Sun's century-long output. Detectors on Soviet Venera spacecraft orbiting Venus, US satellites, and ground-based telescopes all detected the burst. The intensity saturated instruments, initially leading researchers to suspect a nearby gamma-ray event or instrumentation error. Triangulation from multiple detectors localized the source to the Large Magellanic Cloud, confirming an extragalactic origin and indicating extraordinary luminosity. The discovery that neutron stars could produce such energetic bursts led to the magnetar model proposed by Robert Duncan and Christopher Thompson in 1992, attributing soft gamma repeater behavior to ultra-strong magnetic fields in young neutron stars. Soft gamma repeaters number about 30 confirmed sources, with population estimates suggesting roughly 30 million magnetars exist in the Milky Way, about 30% of all neutron stars. Most are dormant, having exhausted their magnetic energy over tens of thousands of years. Young magnetars, less than 10,000 years old, show active bursting. SGR 1806-20 is estimated at 700 years old, based on expansion velocity of an associated supernova remnant. As magnetars age, ohmic dissipation and ambipolar diffusion processes, where magnetic fields diffuse through the crust and core, gradually weaken the field over 10,000 to 100,000 years. Eventually, the field decays to 10 to the 12th or 10 to the 13th Gauss, and the magnetar transitions to a regular pulsar or becomes inactive. The birth rate of magnetars in the galaxy, estimated from supernova rates and the fraction forming magnetars, is roughly 1 per 1,000 years. This predicts 30 million magnetars formed over the Milky Way's 10 billion year history, though most are now inactive or weakly magnetized. The photosphere of a supergiant star. Betelgeuse, the red supergiant marking Orion's shoulder, swells to 700 solar radii, roughly 490 million kilometers across. If placed at the Sun's position, Betelgeuse would engulf Mercury, Venus, Earth, Mars, and extend beyond Jupiter's orbit at 778 million kilometers. This enormous size results from the star's late evolutionary stage. Betelgeuse began life as a massive star around 20 solar masses. Over 10 million years, it burned hydrogen in its core, then expanded and cooled as fusion moved to shells surrounding an inert helium core. The star is currently burning helium in its core and hydrogen in a shell, on its way to carbon burning, the final stage, before core collapse supernova. The expansion decreases surface temperature to approximately 3,500 Kelvin compared to the Sun's 5,778 Kelvin. Despite being cooler, Betelgeuse's enormous surface area makes it luminous, radiating 100,000 times the Sun's power, detectable across interstellar distances. Surface temperature of 3,500 Kelvin places Betelgeuse in spectral class M, the coolest main sequence stars and supergiant class. M-type stars emit most energy in the red and infrared, giving Betelgeuse its distinctive orange-red color visible to the naked eye. The photosphere, the visible surface where photons escape, is not a sharp boundary. In red supergiants, the photosphere transitions gradually over hundreds of thousands of kilometers, from optically thick interior to transparent space. Defining the surface as the radius where optical depth equals 2/3, the point where 2/3 of photons emitted escape directly gives 700 solar radii, but the star has an extensive atmosphere extending beyond this. Spectroscopy detects chromospheric emission from ionized gas at 1,000 solar radii. Dust grains condense at 2 to 3 stellar radii, where temperatures drop below 1,500 Kelvin and molecules like titanium oxide form, providing nucleation sites for grain growth. Luminosity reaches 100,000 solar luminosities, determined from Betelgeuse's apparent brightness and distance. Measuring distance to Betelgeuse is challenging. Parallax measurements from Hipparcos satellite yielded 197 parsecs or 643 light-years, with large uncertainties. More recent ALMA radio interferometry and Gaia parallax suggest 168 parsecs or 548 light-years. Combining distance with observed flux gives bolometric luminosity, total energy emitted across all wavelengths. For red supergiants, bolometric corrections are large because most emission occurs in infrared, not visible light. Betelgeuse's bolometric magnitude is -5.85, compared to apparent visual magnitude 0.5. This 6.35 magnitude difference represents a factor of 400 inches. Flux Betelgeuse emits 400 times more total energy than indicated by visual brightness alone. The 100,000 solar luminosity figure makes Betelgeuse one of the most luminous stars within 1,000 light-years, outshone only by other supergiants and some very massive O-type stars. Mass loss from stellar wind ejects roughly 10 to the -6th solar masses per year, 1/1,000,000th of a solar mass, annually equivalent to losing Earth's mass every 3 years. Red supergiant winds are slower than winds from hotter stars, typically 15 to 20 kilometers per second for Betelgeuse. The mass loss rate times wind velocity gives the mechanical luminosity kinetic energy carried away per second approximately 10 to the 35th ergs per second, negligible compared to radiative luminosity, but significant over stellar lifetimes. Over Betelgeuse's remaining 100,000 years before supernova, it will eject 0.1 solar masses of material, 10% of its current envelope mass. The wind is driven by radiation pressure on dust grains that condense in the cool outer atmosphere. Photons absorbed by dust transfer momentum, accelerating grains outward. Dust drags gas through collisions, creating the wind. This differs from hot star winds driven by line absorption radiation pressure on spectral lines of ionized atoms. Convection cells on Betelgeuse's surface reach sizes comparable to Earth's orbit 100 million kilometers across. Interferometric imaging, using the Very Large Telescope's AMBER instrument and ALMA, resolved bright spots moving across Betelgeuse's disk, interpreted as convection cells rising columns of hot gas bringing energy from interior to surface. Unlike the Sun's granulation convection cells, 1,000 kilometers across covering the surface in a honeycomb pattern, Betelgeuse has only a few giant cells at any time. Each cell rises over months to years, releasing energy at the surface before sinking. The turbulence creates violent motion surface velocities around 50 kilometers per second, causing the photosphere to shift in position by up to 100,000 kilometers. Convection also generates magnetic fields through dynamo processes, though weaker than solar magnetic fields. The combination of convection and magnetic fields drives mass loss, heating the chromosphere and accelerating the wind. The Great Dimming of 2019 to 2020 saw Betelgeuse's brightness drop 35% over several months, sparking speculation it might explode imminently. Betelgeuse normally varies between magnitude 0 and 1.6 over semi-regular periods around 400 days, attributed to pulsations, expansion and contraction driven by opacity changes in the envelope. But in late 2019, brightness plummeted to magnitude 1.6, the faintest recorded in over a century of observation. Speculation ranged from imminent supernova to dust clouds obscuring the star. Follow-up observations using Hubble Space Telescope and ground-based instruments revealed a massive surface mass ejection. A convection cell transported material upward, where it cooled, formed dust, and partially obscured the photosphere from Earth's view. The dust cloud, containing roughly 0.001 solar masses, expanded and dispersed over 2020, and Betelgeuse returned to normal brightness by mid-2020. The event demonstrated that red supergiants can eject significant mass episodically, not just through steady winds. Radiation pressure in Betelgeuse's upper atmosphere exceeds surface gravity, enabling mass loss. Radiation pressure is the momentum flux carried by photons for luminosity L. Radiation pressure force on fully absorbing material is L divided by C times opacity. For Betelgeuse, radiation pressure force exceeds gravitational force beyond about 2 stellar radii, where dust forms. The photosphere itself is marginally bound. Gravitational acceleration at the surface is roughly 0.001 Earth gravities, nearly balanced by radiation pressure on the gas. This makes the photosphere unstable to perturbations. Any density fluctuation increases opacity, which increases radiation pressure, which accelerates material outward, further increasing the fluctuation, a positive feedback runaway. Photospheres of red supergiants are therefore inherently unstable, exhibiting large amplitude pulsations and sporadic ejections. Betelgeuse's photosphere is less a stable surface than a dynamic boundary where inward gravitational force and outward radiation pressure battle continuously. Distance of 548 light-years places Betelgeuse uncomfortably close in astronomical terms. When it explodes as a Type II supernova, inevitable within the next 100,000 years, and possibly much sooner, the event will be spectacular from Earth. Peak brightness will reach magnitude -11 to -12, comparable to the full moon visible during daytime, and casting shadows at night. The supernova will remain visible to the naked eye for months, gradually fading over a year. Neutrinos arrive hours before photons, giving advance warning to detectors like Super Cameo Candé and Ice Cube. Gamma rays and X-rays from the explosion are absorbed by intervening interstellar gas, so they won't threaten Earth. The main danger is cosmic rays' high-energy protons accelerated by the shock wave, but 548 light-years is far enough that cosmic ray flux will increase only marginally. Betelgeuse's eventual death will provide astronomers the closest supernova since Kepler's supernova of 1604, enabling unprecedented detailed observations across the electromagnetic spectrum. Inside a supernova explosion, core collapse begins when the iron core of a massive star reaches the Chandrasekhar limit 1.4 solar masses, the maximum mass supportable by electron degeneracy pressure. Iron is the endpoint of fusion chains. Fusing iron consumes energy rather than releasing it, so no further fusion occurs. As the core accretes iron from silicon burning in shells above, it grows until electron degeneracy can no longer provide sufficient pressure to support it against gravity. Temperature reaches 10 billion Kelvin. At these temperatures, photodisintegration begins. Gamma rays become energetic enough to break iron nuclei apart into helium nuclei and free neutrons, absorbing energy and reducing pressure support. Simultaneously, electron capture electrons combining with protons in nuclei to form neutrons and neutrinos removes electrons that provided degeneracy pressure. Both processes destabilize the core catastrophically. Pressure drops, gravity wins, and the core collapses. The collapse speed reaches 70,000 kilometers per second, 23%, the speed of light, as the core implodes in approximately 1 second. This velocity follows from free fall time, the time for gravitational collapse, which is approximately the inverse square root of density times the gravitational constant. For densities around 10 to the 10th grams per cubic centimeter, typical of pre-collapse iron cores, freefall time is roughly 1 second. The inner core, roughly 0.7 solar masses, collapses homologously, all regions collapsing at the same fractional rate, maintaining density profile. The outer core, roughly 0.7 additional solar masses, collapses supersonically faster than sound speed in the material, so pressure waves cannot propagate outward to slow collapse. The core radius shrinks from 3,000 kilometers to 30 kilometers in 1 second, compressing by a factor of 100 inches radius and 1 million in volume. Density in the inner core skyrockets from 10 to the 10th to 3 times 10 to the 14th grams per cubic centimeter, exceeding nuclear density. Core bounce occurs when the inner core reaches nuclear densities around 2 to 3 times 10 to the 14th grams per cubic centimeter, where neutron degeneracy pressure and nuclear repulsive forces, the short-range strong force preventing nucleons from overlapping halt, collapse abruptly. The equation of state stiffens dramatically at nuclear density pressure, increases far faster than in normal matter. The inner core, now at nuclear density and incompressible, cannot collapse further. But the outer core continues infalling at 70,000 kilometers per second. When infalling material crashes into the rigid inner core, it rebounds, bouncing off the core like a ball hitting a wall. This bounce launches a shock wave, a pressure wave, moving supersonically outward through the infalling material. The shock initially carries enormous energy, roughly 10 to the 51st ergs a foe, short for 51 ergs. For a brief moment, it seems the shock will propagate outward, disrupting the star and causing the supernova. But within milliseconds, the shock stalls. The neutrino burst releases 99% of the supernova's energy, approximately 10 to the 53rd ergs, over roughly 10 seconds. Neutrinos are produced copiously during core collapse through multiple processes. Electron capture during collapse creates electron neutrinos. Once the proto-neutron star forms, It is born hot temperature, 30 billion Kelvin, and cools through neutrino emission. Thermal energy excites neutrino pair production neutrinos and antineutrinos created from thermal photons and nuclear collisions. Roughly 10 to the 58th neutrinos escape, carrying total energy 3 times 10 to the 53rd ergs. By comparison, the kinetic energy of the explosion matter ejected at high velocities is 10 to the 51st ergs. Electromagnetic emission, the visible light, UV, and X-rays totals only 10 to the 49th ergs. Neutrinos are the dominant energy loss, but they interact so weakly that 99% stream through the star without depositing energy. Only 1% of neutrino energy deposited behind the stalled shock through neutrino absorption on neutrons and protons revives the shock and causes the explosion. The shock wave, once revived by neutrino heating, accelerates through the star's envelope at 30,000 km per second, 10% the speed of light. As the shock propagates outward, it heats and compresses the stellar envelope to temperatures reaching 10 billion Kelvin. This heating accelerates fusion material already burning, undergoes explosive fusion on timescales of seconds instead of thousands of years. The shock wave takes hours to days to traverse the envelope, depending on the star's size. For a red supergiant, like Betelgeuse with radius 700 solar radii, the shock takes roughly 3 hours to reach the photosphere. For a blue supergiant with radius 50 solar radii, shock breakout occurs in 1,000 seconds. When the shock reaches the surface and breaks out, it accelerates to nearly light speed as pressure confinement ends. Shock breakout produces an intense flash of UV and X-rays, lasting minutes, the first electromagnetic signal of the explosion. Nucleosynthesis during the explosion creates elements beyond iron, gold, platinum, uranium through rapid neutron capture called the R process. During collapse and explosion, extreme neutron fluxes, densities exceeding 10 to the 24th neutrons per cubic centimeter, bombard seed nuclei. Neutrons are captured faster than beta decays occur, building neutron-rich isotopes that climb the periodic table. Heavy elements like gold 197, platinum 195, and uranium 238 form in seconds. The R process requires neutron-rich conditions impossible in normal stellar burning. Core collapse supernovae and neutron star mergers provide such conditions. Observations of R process element abundances in old metal-poor stars suggest core collapse supernovae were the primary R process site in the early universe. Neutron star mergers contribute significantly as well, confirmed by detection of R process signatures in the kilonova following GW 170817. SN 1987A, the closest supernova to Earth in modern times, exploded on the 23rd of February 1987 in the Large Magellanic Cloud at 168,000 light-years distance. The progenitor star, Sanjalik -69202, was a blue supergiant with mass around 20 solar masses. Neutrino detectors Kamiokande II in Japan and IMB in the United States detected 24 neutrinos in a 13-second burst, arriving 3 hours before the optical brightening, consistent with theoretical predictions. The neutrino detection confirmed core collapse theory and provided constraints on neutrino properties, mass limits, and interaction cross-sections. Optical observations tracked the light curve brightness over time, which rose over 85 days to peak absolute magnitude -15.7, corresponding to 100 million solar luminosities. The light curve shape depends on nickel 5-6 decay produced during explosion. Nickel 5-6 decays radioactively to cobalt 5-6, and then iron 5-6, releasing gamma rays that heat the expanding ejector and power optical emission. The kinetic energy released in core collapse supernovae is approximately 10 to the 51st ergs, 1 faux standard, across most Type II and Type IB I supernovae. This energy expels 10 to 15 solar masses of material at velocities 10,000 to 30,000 kilometers per second. The ejected mass carries momentum and kinetic energy into the interstellar medium, sweeping up ambient gas and creating supernova remnants, expanding shells of hot shocked gas visible for thousands of years. The Crab Nebula, remnant of SN 1054, recorded by Chinese and Arab astronomers, currently spans 11 light-years and expands at 1,500 kilometers per second. Cassiopeia A, remnant from a supernova around 1,680, shows filamentary structure and clumpy ejecta indicating asymmetric explosion. Core collapse supernovae, visible across the observable universe, detected at redshifts exceeding 1 SeV as probes of cosmic expansion and stellar evolution across cosmic history. A gamma-ray burst jet stream. GRB 080916C stands as the most powerful explosion ever detected by humanity, releasing an isotropic equivalent energy of 5.4 times 10 to the 54th ergs, 540 times the canonical supernova energy of 10 to the 51st ergs, or 540 Fo. Detected by the Fermi Gamma Ray Space Telescope on the 16th of September 2008, the burst originated from redshift Z equals 4.35, corresponding to a distance of 12.2 billion light-years when the universe was only 2.1 billion years old. The isotropic energy assumes the burst radiated equally in all directions, but gamma-ray bursts are beamed concentrated into narrow jets with opening angles 1 to 10 degrees. Accounting for beaming, the true energy released is reduced by roughly a factor of 100 to 1000, yielding roughly 10 to the 52nd to 10 to the 53rd ergs, still exceeding typical supernovae by factors of 10 to 100. This energy emerged during the burst's active phase, lasting approximately 60 seconds, giving a luminosity around 10 to the 52nd ergs per second, outshining all stars in the observable universe combined. Jet speeds in gamma-ray bursts reach 99.99% the speed of light, characterized by Lorentz factors gamma the time dilation and length contraction factor from special relativity exceeding 1000. A Lorentz factor of 1000 means the jet material moves at 0.9999995 times the speed of light. At these velocities, time dilation slows the jet's internal clock by a factor of 1000 compared to stationary observers. Lengths contract by the same factor. A 1,000-kilometer object moving at this speed appears only 1 kilometer long in the direction of motion. Such extreme velocities arise from the collapsor mechanism core collapse of a rapidly rotating massive star to a black hole surrounded by an accretion disk. Energy extracted from accretion and black hole rotation via the Blandford-Znajek process launches jets along the rotation axis. These jets bore through the collapsing star, erupting from the surface and accelerating to ultra-relativistic speeds. Opening angles of gamma-ray burst jets range from 1 to 10 degrees, determined through afterglow observations and jet break features in light curves. When a jet expands, its edges eventually become visible to observers along the jet axis. This causes the afterglow brightness to decline more steeply at jet break. The time of the jet break depends on jet opening angle and bulk Lorentz factor. Typical opening angles around 5 degrees mean the jet covers roughly 1 part in 2,000 of the sky. A solid angle, 0.005 steradians, compared to 4 pi or 12.6 steradians for the full sky. Beaming reduces the required isotropic energy by factors of a few hundred. GRB 080916C's beaming corrected energy is approximately 10 to the 50-second ergs. Beaming also means most gamma-ray bursts point away from Earth and go undetected. For every burst we detect, roughly 500 occur, but remain invisible because their jets don't aim toward us. The collapsar model explains long-duration gamma-ray bursts, those lasting more than 2 seconds, through core collapse of massive stars with rapid rotation. Stars more massive than 25 solar masses, with rotation periods below 10 seconds at the time of core collapse, are candidates. When the iron core collapses, it forms a black hole rather than a neutron star if mass exceeds 2.5 to 3 solar masses. The star's envelope continues collapsing onto the black hole, forming an accretion disk. This disk accretes at super Eddington rates exceeding 10 solar masses per second, initially releasing enormous power through gravitational potential energy conversion. Roughly 10% of accreted mass energy becomes jet energy through processes extracting rotational energy from the black hole and disk. The jets, confined initially by the collapsing star, bore through thousands of kilometers of stellar material. Only if the star's envelope is relatively compact, a blue supergiant or Wolf-Rayet star stripped of its hydrogen envelope, can jets escape before losing energy. Duration varies dramatically across gamma-ray burst populations. Long bursts last 2 to 1,000 seconds, with typical durations around 30 seconds. Short bursts last 0.01 to 2 seconds, with typical durations 0.3 seconds. Long bursts arise from massive star core collapse. Short bursts result from neutron star merges two neutron stars, or a neutron star and black hole merging, creating a black hole surrounded by a temporary accretion disk formed from tidally disrupted neutron star material. The short burst duration reflects the limited mass available in the disk and the rapid timescale of accretion. GW170817, the neutron star merger detected by LIGO on the 17th of August 2017, produced a short gamma-ray burst detected 1.7 seconds after merger by Fermi and integral satellites, confirming the merger origin of at least some short bursts. The sterilization radius, the distance within which a gamma-ray burst would destroy complex life, is approximately 3,000 light-years. For a typical long burst with isotropic energy 10 to the 51st ergs, and a beaming factor 500. Within this radius, the gamma-ray and X-ray flux from the burst would deposit roughly 100 kilojoules per square meter at Earth's orbital distance from the Sun. This energy ionizes and heats the atmosphere, dissociating nitrogen and oxygen molecules and producing nitrogen oxides that catalytically destroy ozone. Ozone depletion allows solar ultraviolet radiation to reach the surface at lethal intensities. Additionally, cosmic rays accelerated by the burst's blast wave arrive over subsequent years, further damaging the atmosphere and irradiating the surface. Complex multicellular life would face mass extinction. Microbial life in oceans and subsurface environments might survive, but surface ecosystems would collapse. The Ordovician extinction, occurring 450 million years ago and eliminating roughly 85% of marine species, has been tentatively linked to a nearby gamma-ray burst. The extinction coincided with evidence of ozone layer depletion, increased UV radiation damaging organisms, and triggering a glaciation period through atmospheric chemical changes. Researchers proposed a gamma-ray burst within 3,000 to 6,000 light-years could explain the observations. The burst would need to have occurred in our galaxy or nearby extragalactic bursts at megaparsec distances are too distant to threaten Earth. Galactic gamma-ray burst rates are estimated at 1 per 100,000 to 1 million years based on core collapse supernova rates and the fraction that produce gamma-ray bursts. The nearest known gamma-ray burst candidate progenitor is WR104, a Wolf-Rayet star 8,000 light-years away, potentially aimed at Earth, based on its rotating pinwheel nebula structure. Detectability across the universe makes gamma-ray bursts among the most distant objects observable. The most distant confirmed gamma-ray burst, GRB 090423, occurred at redshift Z equals 8.2, corresponding to 13.04 billion light-years, when the universe was 630 million years old. Despite the enormous distance, the burst was detected by Swift satellite and followed up by ground-based telescopes measuring the redshift through absorption lines from neutral hydrogen in the intergalactic medium. High redshift gamma-ray bursts serve as probes of the early universe. Their afterglows illuminate the gas between us and the burst, revealing chemical compositions, ionization states, and large-scale structure during cosmic dawn when the first stars and galaxies formed. Future gamma-ray observatories, like SVOM and Einstein probe, will detect bursts at even higher redshifts, potentially reaching Z equals 10 to 15, observing explosions from the very first generation of stars. Gamma-ray burst jets viewed from within would be an environment of unimaginable horror. The jet interior contains ultra-relativistic plasma electrons, positrons, protons moving at 9,999% light speed, with Lorentz factors exceeding 1,000. Temperatures reach trillions of Kelvin. Magnetic fields exceed 10 to the 15th Gauss, even stronger than magnetars. Radiation energy density is so extreme that photon-photon collisions produce electron-positron pairs copiously, creating a pair-dominated plasma. The radiation spectrum peaks in gamma rays with energies megaelectron volts to gigaelectron volts, millions to billions of times more energetic than visible light photons. Internal shocks, collisions between faster and slower moving jet components, dissipate kinetic energy into radiation, powering the observed burst. Any matter caught in the jet would be instantly vaporized, ionized, and accelerated to relativistic speeds, incorporated into the jet flow, and ultimately radiated away as gamma rays. The accretion disk of a quasar. 3C273, the first quasar discovered and still among the brightest, radiates 10 to the 40th watts of power, 4 trillion times the Sun's luminosity, from a region smaller than the solar system. Located 2.4 billion light-years away, 3C273 was identified in 1963 by Martin Schmidt, who measured its redshift at Z equals 0.158, establishing it as extragalactic and requiring enormous luminosity to appear as bright as faint stars despite vast distance. The name quasar derives from quasi-stellar radio source. These objects appeared star-like in optical images, but emitted powerful radio waves and showed unusual spectra with broad emission lines at unfamiliar wavelengths, later recognized as redshifted hydrogen and other elements. 3C273's luminosity requires a supermassive black hole approximately 1 billion solar masses, accreting matter at roughly 10 solar masses per year. This accretion rate approaches the Eddington limit, the maximum sustainable accretion rate, before radiation pressure halts further infall. Distance of 2.4 billion light-years places 3C273 inches, the relatively nearby universe compared to the most distant quasars, exceeding 13 billion light-years. The quasar's brightness apparent magnitude 12.8 inches optical wavelengths makes it detectable with amateur telescopes, unusual for such distant objects. Most quasars require large professional telescopes. The relative proximity enables detailed study optical and infrared interferometry resolve the accretion disk and dusty torus. X-ray observations detect spectral features from the innermost disk regions within 10 Schwarzschild radii of the black hole. The jet, extending over 200,000 light-years, shows knots and hotspots indicating shocks and particle acceleration sites. 3C273 has been monitored continuously for decades, revealing variability on timescales from hours to years. Rapid variability constrains emission region size through causality regions larger than light travel time. Time's variability timescale cannot vary coherently. Hour-long X-ray flares indicate emission from regions only light hours across, comparable to Pluto's orbital size. Accretion rates reaching 10 solar masses per year seem enormous, but they're typical for luminous quasars with billion solar mass black holes. The Eddington accretion rate, the rate at which radiation pressure balances gravity, preventing further infall, is approximately 20 solar masses per year for a 1 billion solar mass black hole, assuming 10% radiative efficiency. 3C273 accreting at 10 solar masses per year operates at roughly 50% of Eddington. The accretion disk converts gravitational potential energy to radiation with 10% efficiency for a non-rotating black hole, increasing to 40% for maximally rotating Kerr black holes. Material falling into the black hole from infinity releases energy equal to efficiency times m times c squared. For 10 solar masses per year with 10% efficiency, power output is 10 to the 40th watts. This requires a continuous gas supply. 10 solar masses per year depletes 10 billion solar masses in 1 billion years, explaining why quasars are rare in the nearby universe where gas supplies are depleted. Temperature gradients across the accretion disk span orders of magnitude from 10 million Kelvin at the innermost stable circular orbit to 10,000 Kelvin in the outer disk, hundreds of astronomical units from the black hole. Temperature at radius r scales as r to the -3/4 power in the standard thin disk model. For a 1 billion solar mass black hole, the innermost stable orbit lies at 3 Schwarzschild radii, about 9 billion kilometers, or 60 astronomical units. At this radius, orbital velocity reaches 50% light speed, and orbital period is roughly 1 day. Temperature peaks at 10 million Kelvin, producing soft X-rays. At 100 astronomical units, temperature drops to 100,000 Kelvin, emitting far ultraviolet. At 1,000 astronomical units, temperature reaches 10,000 Kelvin, emitting optical and near ultraviolet. The outer disk extending to 0.1 parsecs, 20,000 astronomical units, emits infrared at temperatures below 1,000 Kelvin. Multi-wavelength observations detect this spectrum, confirming accretion disk models. Radiation pressure approaches the Eddington limit in the innermost disk regions where luminosity peaks. The Eddington luminosity, L Eddington, equals 4 pi g m protons c divided by sigma Thomson, where sigma Thomson is the Thomson scattering cross-section for photons scattering off electrons. For a billion solar mass black hole, L Eddington equals 1.3 times 10 to the 47th ergs per second. 3C273's 10 to the 47th ergs per second, luminosity reaches 80% of Eddington. In the inner disk, radiation pressure on gas through Thomson scattering becomes comparable to gravitational force. This limits accretion rates. If too much mass falls inward, radiation pressure exceeds gravity and halts infall. Super Eddington accretion can occur if radiation is trapped in optically thick flows, unable to exert full pressure. Slim disk models describe such flows, allowing accretion rates exceeding Eddington by factors of 10 to 100 inches, the most extreme cases. Relativistic jets extending 300,000 light-years from 3C273's nucleus carry enormous power, estimated at 10 to the 46th ergs per second, roughly 10% of the total accretion luminosity. The jets launch perpendicular to the accretion disk, likely through the Blandford-Zinayak process, extracting rotational energy from the spinning black hole via magnetic fields threading the event horizon. Jet material moves at speeds exceeding 99% light speed, with bulk Lorentz factors around 10 to 30. The jets terminate in radiolobes regions, where jet kinetic energy dissipates through shocks, heating gas, and accelerating particles to relativistic energies. These particles emit synchrotron radiation electromagnetic waves, produced when electrons spiral in magnetic fields detected at radio frequencies. Knots along the jet show superluminal motion, apparent velocities exceeding light speed, a relativistic effect where material moving at high speeds nearly along the line of sight appears faster than light due to light travel time. Differences. The broad line region, extending 0.01 to 0.1 parsecs from the nucleus, contains gas clouds moving at velocities 5,000 to 20,000 kilometers per second around the black hole. These clouds emit strong emission lines, hydrogen Balmer lines, magnesium-2, carbon-4, broadened by Doppler shifts from their rapid motion. Reverberation mapping measuring time delays between continuum variations from the accretion disk and responding emission line variations from the broad line region determines the region's size. Light travel time delays of days to weeks indicate sizes 0.01 to 0.1 parsecs. Combining size with velocity from line widths yields the black hole mass through virial theorem velocity squared times radius divided by the gravitational constant. For 3C273, this gives roughly 1 billion solar masses, consistent with other mass determination methods, including accretion disk modeling and host galaxy dynamics. Ionizing radiation from the accretion disk strips electrons from atoms across enormous volumes surrounding the quasar. Photons, with energies exceeding 13.6 electron volts, the hydrogen ionization energy ionize hydrogen atoms, creating HII regions, ionized hydrogen zones, extending thousands to tens of thousands of light years. More energetic photons ionize heavier elements helium requires, 24.6 electron volts, carbon 11.3 electron volts, oxygen 13.6 electron volts. The ionizing photon flux from a luminous quasar, like 3C273, exceeds 10 to the 56th photons per second. These photons propagate outward, encountering and ionizing gas throughout the quasar's host galaxy and beyond. The ionization parameter, ionizing photon density, divided by gas density, determines ionization state. High ionization parameters strip multiple electrons from atoms, creating highly ionized species like OIII, NEV, Phe-V7, observed spectroscopically. Quasars ionize intergalactic gas across megaparsec scales, contributing to the ionization of the universe during reionization epochs. A Wolf-Rayet star's stellar wind. WR102, a Wolf-Rayet star in the constellation Sagittarius, blazes at a surface temperature of 250,000 Kelvin, 44 times hotter than the Sun's 5,778 Kelvin surface. With a mass around 32 solar masses remaining after shedding much of its original 60+ solar mass envelope, WR102 represents the final evolutionary stage before core collapse supernova. Wolf-Rayet stars have stripped away their outer hydrogen layers through powerful stellar winds, exposing helium-burning cores. WR102 spectrum shows strong emission lines from highly ionized helium, carbon, nitrogen, and oxygen, with virtually no hydrogen, indicating complete envelope loss. The extreme temperature results from the exposed core-burning helium into carbon and oxygen at rates exceeding 10 to the 38th ergs per second, hundreds of thousands of solar luminosities. At this temperature, the star emits most energy as extreme ultraviolet and soft X-rays, invisible to optical telescopes but detected by space-based UV and X-ray observatories. Mass loss from Wolf-Rayet winds reaches 10 to the -5th solar masses per year. 10 Earths of material expelled annually. This rate is 100 times greater than red supergiant winds and 10 million times greater than the solar wind's 10 to the minus 14th solar masses per year. Over the Wolf-Rayet phase, lasting 100,000 to 1 million years, the star ejects 10 to 30 solar masses, evacuating its entire hydrogen envelope. The wind velocity reaches 2,000 to 3,000 kilometers per second, 1%, the speed of light driven by radiation pressure on spectral lines of ionized carbon, nitrogen, and oxygen. The mechanical luminosity kinetic power in the wind is approximately 10 to the 38th ergs per second, comparable to the star's radiative luminosity. This wind collides with previously ejected material and interstellar gas, creating wind-blown bubbles expanding shells of shocked gas spanning parsecs, visible as nebulae surrounding Wolf-Rayet stars. WR-104, located 8,000 light-years away, exhibits a spectacular pinwheel nebula formed by its stellar wind colliding with wind from a binary companion star, an OB supergiant. The two stars orbit with a 220-day period, and their winds collide in the orbital plane, creating a shock front. Dust condenses in the cooled post-shock gas at temperatures around 1,500 Kelvin. As the binary orbits, the dust spiral pattern rotates, creating the pinwheel appearance. Observations using the Keck telescope's infrared interferometer resolved the pinwheel's structure with milliarc-second resolution, showing the spiral extends roughly 200 astronomical units. The pinwheel's orientation viewed nearly face-on from Earth has raised concerns that WR-104's rotation axis might point toward us. If the axis aligns within a few degrees of our line of sight, the eventual core collapse supernova could produce a gamma-ray burst jet aimed at Earth. The potential gamma-ray burst progenitor status of WR-104 depends on its rotation rate and axis orientation. Gamma-ray bursts require rapid rotation periods below 10 seconds to produce the accretion disk and magnetic fields necessary for jet launching. WR-104's rotation period is not directly measured, but spectroscopic line profiles suggest rotational velocities around 500 kilometers per second. For a radius 5 solar radii, this implies periods around 2 to 5 days, far too slow for gamma-ray burst production. However, core rotation can differ from envelope rotation. If the core rotates rapidly while the envelope rotates slowly, gamma-ray burst production remains possible. The axis orientation is inferred from the pinwheel's face-on appearance, suggesting the axis is within 30 degrees of our line of sight. If aligned within 5 degrees and core rotation is rapid, WR-104's supernova could produce a burst partially aimed at Earth, though likely too weak to cause extinction from 8,000 light-years. Lifetimes of Wolf-Rayet stars range from 100,000 to 1 million years, depending on initial mass and mass loss rates. More massive stars evolve faster. A 100 solar mass star spends only 100,000 years as a Wolf-Rayet before exploding. Less massive stars around 25 to 30 solar masses might persist 1 million years. WR-102's 3.2 solar mass current mass suggests it originated around 60 to 80 solar masses and has been a Wolf-Rayet for perhaps 300,000 to 500,000 years. It could explode tomorrow or in another 500,000 years, timescales short astronomically but too uncertain for prediction. The explosion will be visible from Earth as a type IB or IG supernova core collapse, supernovae lacking hydrogen due to envelope stripping. Peak brightness will reach absolute magnitude -18, appearing as bright as the full moon from Earth despite 25,000 light-year distance to the galactic center region where many Wolf-Rayet stars cluster. CNO-processed material visible in Wolf-Rayet spectra reveals nuclear burning products from the star's core. The CNO cycle, carbon-nitrogen-oxygen fusion cycle, converting hydrogen to helium, operates in massive stars' cores. This cycle alters isotopic ratios. Carbon 1,2 converts to nitrogen 1,4, nitrogen 1,5 converts to oxygen 1,6 through various reaction chains. When the envelope is stripped, these processed materials appear at the surface. WR102 shows strong nitrogen emission lines, with nitrogen to carbon ratios exceeding 10 far above solar ratios, where nitrogen and carbon are comparable. Some Wolf-Rayet stars show carbon-rich compositions classified as WC stars, indicating helium burning has progressed to carbon production. Others show nitrogen-rich compositions, WN stars, representing earlier stages. WR102 is a WN star. Spectroscopy thus probes nuclear burning deep inside stars, revealing evolution in real time. UV radiation output from Wolf-Rayet stars exceeds solar UV by factors exceeding 100,000. The Sun emits roughly 10 to the 33rd ergs per second total, with about 10% in UV wavelengths below 400 nanometers. WR102 at 250,000 Kelvin emits most energy as UV approximately 10 to the 39th ergs per second. This intense UV ionizes surrounding gas out to parsec scales, creating massive HI regions ionized hydrogen nebulae. The Carina Nebula complex, containing dozens of Owen Wolf-Rayet stars including Eta Carinae, spans 300 light-years and is ionized primarily by UV from its massive stellar population. Within 1 astronomical unit of WR102, UV flux exceeds 10 to the 14th ergs per square centimeter per second, enough to vaporize any solid material instantly. Planets, if they existed, would be stripped to bare rock cores or evaporated entirely. Life anywhere near a Wolf-Rayet star is impossible. The Orion Nebula core. The Orion Nebula, officially designated Messier 42 or NGC 1976, lies 1,344 light-years from Earth in the Sword region of Orion constellation, making it the nearest massive star-forming region and one of the most studied objects in astronomy. The nebula spans approximately 24 light-years across, though its ionized gas extends farther and contains sufficient mass to form thousands of solar mass stars. At its heart lies the Trapezium cluster, a tight grouping of 4 bright stars visible in small telescopes, with dozens of additional members resolved in infrared observations. The cluster is extremely young, at roughly 1 to 2 million years old, containing stars still accreting material from their natal disks and surrounded by the remnants of the molecular cloud that birthed them. The trapezium represents the first stage of stellar birth, where massive O and B-type stars have formed and begun ionizing their surroundings, while lower mass stars continue forming in dense cloud cores shielded from the intense radiation. Theta 1 Orionis C, the brightest and most massive trapezium member, dominates the nebula's energy budget. This O6-type main sequence star contains approximately 40 solar masses, compressed into a radius only 12 solar radii, far denser than the Sun, despite being more massive. Surface temperature reaches 45,000 Kelvin, making it emit most energy as extreme ultraviolet radiation, invisible to human eyes. The star's luminosity totals 200,000 solar luminosities, with roughly 90% emerging as ionizing photons with energies exceeding 13.6 electron volts, sufficient to strip electrons from hydrogen atoms. These photons flood the surrounding gas at rates exceeding 10 to the 49th per second, creating the Strömgren sphere, the ionized region where ionization rate equals recombination rate. For Theta 1 Orionis C, this sphere extends roughly 10 light-years, encompassing most of the visible nebula. UV flux in the nebula's core exceeds the solar neighborhood's intensity by factors of 100,000. Near Earth, the ambient UV radiation field from distant stars produces roughly 10 to the minus third ergs per square centimeter per second. At 0.1 parsecs, 0.3 light-years, from Theta 1 Orionis C, UV flux reaches 10 ergs per square centimeter per second, 10 million times higher. This intense radiation ionizes all hydrogen within its reach, heats gas to 10,000 Kelvin through photoelectric heating, and photodissociates molecules, breaking chemical bonds. Organic molecules that might form in cooler regions are instantly destroyed by UV photons. The environment is completely hostile to complex chemistry. Only the simplest molecules, like carbon monoxide, survive in shielded regions, and even these dissociate if exposed to direct starlight. Life as we know it cannot exist in such conditions. Even extremophile bacteria would be sterilized instantly by the UV flux. Proplied's protoplanetary disks around young stars number over 150 inches Hubble Space Telescope imaging of the Orion Nebula core. These disks, typically 100 to 1,000 astronomical units in diameter, contain the gas and dust from which planets would form in quiescent environments. But in Orion's hostile core, UV radiation from Theta 1 Orionis C evaporates the disks through photoevaporation. UV photons heat disk surfaces to thousands of Kelvin, giving atoms and molecules enough thermal energy to escape the weak gravitational field of the young star, typically 0.5 solar masses with escape velocities only a few kilometers per second. Mass loss rates reach 10 to the minus 7th to 10 to the minus 6th solar masses per year. At these rates, disks containing 0.01 solar masses, the minimum needed for giant planet formation, evaporate in 10,000 to 100,000 years. Many Orion disks are visibly evaporating in Hubble images, showing bright ionization fronts where UV radiation impacts the disk surface and cometary tails of evaporated gas streaming away. Temperatures in the ionized gas reach 10,000 Kelvin, determined by the balance between photoheating and cooling processes. Photoheating occurs when UV photons ionize hydrogen, ejecting electrons with kinetic energies equal to photon energy minus ionization energy. For photons just above the 13.6 electron-volt threshold, electrons gain little energy. For more energetic photons, electrons gain several electron volts, translating to temperatures 10,000 to 20,000 Kelvin. Cooling occurs through recombination electrons, recombining with protons to form neutral hydrogen, radiating energy as Balmer and Lyman series photons, and collisionally excited line emission from trace elements like oxygen, nitrogen, and sulfur. The balance settles around 10,000 Kelvin for typical HI region conditions. At this temperature, gas pressure is roughly 10,000 times atmospheric pressure at Earth's surface. Despite densities only 100 to 1,000 hydrogen atoms per cubic centimeter, the high temperature compensates for low density, maintaining pressure. The environment destroys forming planetary systems through multiple mechanisms. Photoevaporation removes disk mass faster than planets can form, preventing planet assembly. For giant planets forming through core accretion where rocky cores accrete gas envelopes, evaporation removes gas before envelopes can grow massive. For terrestrial planets, photoevaporation might actually help by removing gas and leaving behind rocky material, but the intense UV flux prevents organic chemistry and water retention. Any atmospheres that form are stripped immediately. Additionally, dynamical interactions in the dense cluster environment eject planets through gravitational scattering. Close encounters between stars occurring frequently in clusters with stellar densities 1,000 times the solar neighborhood perturb planetary orbits, sending planets into eccentric orbits or ejecting them entirely. Orion's core is thus a planetary graveyard, where disks evaporate and any planets that form are destroyed. Star formation continues despite the hostile radiation environment, with new stars forming at roughly 1 solar mass per 100,000 years averaged over the nebula. This rate is modest compared to giant molecular clouds containing 100,000 solar masses forming stars at solar masses per year, but Orion is relatively small, and much of its gas has already been ionized or dispersed. Star formation occurs in dense molecular cores within the larger Orion molecular cloud complex regions, where gas densities exceed 10,000 molecules per cubic centimeter, and visual extinction exceeds 10 magnitudes, shielding interiors from UV radiation. These cores gravitationally collapse over 100,000-year timescales, fragmenting into protostellar clumps that accrete surrounding gas. Once protostars become massive enough to ignite fusion, they emerge from their natal clouds as pre-main sequence stars surrounded by accretion disks, the Prepleiades visible throughout the nebula. Orion serves as a laboratory for studying stellar birth in hostile radiation environments, revealing how massive star formation affects subsequent generations. Observations show that star formation is self-limiting UV radiation from massive stars, heats and ionizes surrounding gas, increasing pressure and preventing further gravitational collapse. The expanding HI region sweeps up neutral gas into a dense shell at the ionization front. This shell becomes gravitationally unstable and fragments, triggering a new generation of star formation at the periphery, a process called triggered star formation. Evidence for this appears in Orion's age gradient. The trapezium stars at the center are youngest at 1 million years, while stars at the nebula's edge are slightly older at 2 to 3 million years, suggesting sequential formation propagating outward. Eventually, the ionizing stars die as supernovae, disrupting the cloud and terminating star formation, leaving a cluster of stars to disperse into the galactic field. Inside the Crab Nebula Pulsar Wind, PSR B 531+21, discovered in 1968 as the pulsar within the Crab Nebula and confirmed as the neutron star remnant of the 1054 supernova, spins 30.2 times per second with a period of 33.085 milliseconds. This rapid rotation makes the Crab one of the fastest pulsars known outside the millisecond pulsar population. The spin rate decreases measurably, period increasing 38 nanoseconds per day, as the pulsar loses rotational energy through electromagnetic radiation and particle acceleration. The energy loss rate, calculated from the period derivative, reaches 4.5 times 10 to the 38th ergs per second, equivalent to 100,000 solar luminosities. This energy doesn't vanish. It flows into the pulsar wind, a relativistic outflow of electrons, positrons, and electromagnetic fields streaming away from the pulsar at nearly light speed, filling the Crab Nebula with energy and powering its multi-wavelength emission. The pulsar wind radiates 4.5 times 10 to the 38th ergs per second, making it the most powerful continuous energy source in the Crab Nebula system. This power exceeds the supernova explosion's energy output averaged over the 970 years. Since explosion, the supernova released roughly 10 to the 51st ergs total over seconds to months, corresponding to average power 10 to the 37th ergs per second if spread over 1,000 years. The pulsar's current output exceeds this, dominating the nebula's energy budget. The energy emerges as relativistic plasma-electron-positron pairs with Lorentz factors, hundreds to thousands, and electromagnetic fields. Magnetic field lines anchored to the neutron star's surface rotate with it, generating enormous electric fields that accelerate particles to ultra-relativistic energies. These particles stream outward along open magnetic field lines, forming the pulsar wind that fills the interior of the supernova remnant. The wind terminates at the Crab's termination shock, located roughly 0.1 light-years 1/10 of a light-year or 6,000 astronomical units from the pulsar, visible in X-ray and optical images as a bright ring surrounding the pulsar. At the shock, the relativistic cold wind, cold meaning highly ordered, with little random motion, despite ultra-relativistic speeds, collides with slower-moving supernova ejecta expanding at 1,500 kilometers per second. The collision creates a shock wave where directed kinetic energy converts to random thermal energy and accelerates particles to even higher energies. The shock is not a smooth boundary, but a turbulent interface with complex structure, varying on timescales from days to months, as observed in Chandra X-ray movies, showing moving knots and jets. The termination shock defines the boundary between pulsar-dominated regions inside and supernova-dominated regions outside. Particle acceleration at the termination shock produces electrons and positrons with energies reaching teri-electron volts, trillion electron volts, or 10 to the 12th eV. These ultra-high energy leptons produce the crab's observed emission through synchrotron radiation and inverse Compton scattering. Synchrotron radiation occurs when charged particles spiral in magnetic fields, emitting photons perpendicular to their spiral motion. The synchrotron spectrum extends from radio through optical to X-rays, with photon energy proportional to particle energy squared times magnetic field strength. Observing X-ray synchrotron emission at 10 keV requires electron energies around 10 to the 12th eV in 100 microgauss magnetic fields. Inverse Compton scattering occurs when ultra-relativistic electrons collide with low-energy photons such as optical synchrotron photons or cosmic microwave background photons, boosting them to gamma-ray energies. The crab emits gamma rays up to 100 GeV through this process, detected by ground-based Cherenkov telescopes like VERITAS and HESS. The magnetic field at the termination shock reaches approximately 100 microgauss, 10 to the -4th Gauss. This field is far weaker than the neutron star's surface field of 10 to the 12th Gauss, but stronger than the galactic interstellar field of 5 microgauss. The field strength is inferred from synchrotron emission, observing photon energy distribution and particle energies derived from other measurements, allows calculating field strength through synchrotron theory. The field is highly structured, showing loops, arcs, and jets in polarized optical and X-ray images. Magnetic field geometry reflects the pulsar's rotating magnetosphere and the complex shock structure. Time variability in polarization and intensity indicates the field reorganizes continuously through reconnection and turbulence, releasing additional energy bursts that brighten specific nebular regions episodically. The Crab Nebula glows across the electromagnetic spectrum from radio to gamma rays, making it one of few objects bright at all wavelengths. Radio emission at 1 to 10 GHz comes from synchrotron radiation from relatively low-energy electrons, detected by radio telescopes like the VLA. Infrared emission at 10 microns traces warm dust mixed with the synchrotron continuum. Optical emission, giving the nebula its namesake crab-like appearance in Lord Ross's 1844 drawing, combines synchrotron continuum with emission lines from hydrogen, helium, oxygen, and sulfur in the slower-moving ejecta. X-rays at 1 to 10 keV, imaged spectacularly by Chandra, show synchrotron radiation from multi-TeV electrons near the termination shock. Gamma rays at megaelectron volt to gigaelectron volt energies from Fermi satellite and TeV energies from ground-based telescopes reveal inverse Compton processes. This pan-spectral emission makes the crab the standard candle for calibrating astronomical instruments across wavelengths. The pulsar spins down measurably, with period increasing 38 nanoseconds per day, corresponding to spin-down rate approximately 1.3 billionths of a second per year. Over human timescales, this is tiny. The pulsar's period has increased only 40 microseconds since its 1968 discovery. But over the 970 years since the supernova, the period has lengthened noticeably. Extrapolating backward, assuming constant spin-down rate, suggests an initial period around 19 milliseconds at birth, spinning twice as fast as today. In reality, spin-down rate decreases as the pulsar slows, so the initial period was likely even shorter, perhaps 10 to 15 milliseconds. Observations constrain spin-down through precise timing, measuring pulse arrival times at radio telescopes with microsecond precision over decades. The Jodrell Bank Observatory has monitored the crab continuously since 1984, measuring period derivatives and detecting glitches, sudden spin-up events, where the pulsar period decreases abruptly by microseconds, then slowly recovers, attributed to crustal fractures or superfluid vortex unpinning in the neutron star interior. Electromagnetic braking extracts rotational energy, converting it to pulsar wind power through magnetic dipole radiation. A rotating magnetic dipole emits electromagnetic waves carrying energy away, spinning down the source. The spin-down power is proportional to the square of the magnetic field strength times the fourth power of rotation rate. For the crab's surface magnetic field, 10 to the 12th Gaussian rotation period 33 milliseconds, this yields precisely the observed 4.5 times 10 to the 38th ergs per second, confirming electromagnetic braking as the dominant energy loss mechanism. As the pulsar spins down, both magnetic dipole radiation and pulsar wind power decline proportional to rotation rate to the fourth power. In another 1,000 years, the crab pulsar will have slowed significantly, reducing power output by factors of several. In 10,000 years, it will resemble typical pulsars with periods hundreds of milliseconds and much lower power. The nebula fading as energy input declines and synchrotron-emitting electrons radiate away their energy. A rogue planet in interstellar space. PSOJ 318 5-22. Discovered in 2013 by the Pan-STARRS survey using visible and near-infrared imaging, drifts through interstellar space 80 light-years from Earth with no parent star illuminating it. With a mass 6.5 times Jupiter's, this object straddles the boundary between massive planet and brown dwarf failed stars that never achieved fusion. PSOJ 318 5-22 shows spectral features similar to young gas giant planets orbiting stars, including water vapor, methane, and molecular hydrogen absorptions, but it wanders alone through the galaxy. The object's age, estimated at 12 million years from its spectrum and kinematics, suggests it formed like a star from direct gravitational collapse of a gas cloud, or was ejected from a planetary system shortly after formation. Without stellar heating, PSOJ 318 5-22 relies solely on residual heat from formation gravitational potential energy released during collapse to maintain its temperature. Surface temperature reaches 1,100 Kelvin, hot enough to glow dull red if visible to human eyes, though most emission occurs in infrared wavelengths, invisible without instruments. This temperature results from contraction and residual formation, heat slowly radiating away. Young massive planets and brown dwarfs cool predictably, following evolutionary tracks calculated from atmospheric and interior models. PSOJ 318 5-22's luminosity is approximately 10 to the -5th solar luminosities, 10,000 times dimmer than the Sun, powered by gravitational contraction at rate roughly 1 Earth radius per million years. As the object contracts, gravitational potential energy converts to thermal energy, balancing radiation losses. Over tens of millions of years, temperature will decline to 500 Kelvin, then 300 Kelvin, eventually reaching equilibrium with the cosmic microwave background at 2.7 Kelvin after several billion years, though residual radioactive heating might maintain slightly higher temperatures indefinitely. The coldest known rogue, 2-mass J1000, 119-1137, has cooled to 225 Kelvin, slightly below water's freezing point, making it one of the coolest directly observed substellar objects. Discovered through 2-micron all-sky survey infrared data, this object has mass estimated between 5 and 10 Jupiter masses, an age possibly exceeding 1 billion years based on its cool temperature. Spectroscopy shows ammonia absorption, ammonia condenses, at temperatures below 200 Kelvin at Jovian atmospheric pressures, indicating high-altitude clouds of solid ammonia ice. The object emits faintly in mid-infrared wavelengths, but is undetectable in visible light, requiring sensitive infrared instruments for observation. Such cold rogues represent the final evolutionary stage of free-floating substellar objects, approaching thermal equilibrium with interstellar space and becoming nearly invisible except through gravitational effects or faint infrared glow. Population estimates suggest 2 to 3 times more rogue planets than stars populate the galaxy, implying trillions of wandering worlds in the Milky Way alone. These estimates derive from microlensing surveys detecting rogue planets when they pass in front of background stars, magnifying starlight through gravitational lensing. The MOA and OGLE surveys, monitoring millions of stars towards the galactic bulge, detect roughly 1 planet mass lensing event per few million star years of monitoring. Extrapolating from detection rates and accounting for survey sensitivity limitations yields population estimates. Microlensing detects planets between 0.3 and 10 Jupiter masses most efficiently, likely missing Earth mass rogues that produce briefer, fainter signals. If rogue planet mass distribution resembles bound planet distributions, Earth mass rogues might outnumber Jupiter mass rogues by factors of 10, implying tens to hundreds of trillions of Earth mass rogues wander the galaxy. Formation mechanisms include gravitational ejection during planetary system formation, or direct collapse of gas clouds. Ejection occurs when planetary systems contain multiple giant planets whose gravitational interactions become unstable. Close encounters scatter planets, ejecting the lightest while others move to tighter orbits. Simulations of planetary system evolution show that systems initially containing 3 to 5 giant planets often eject 1 or 2 while stabilizing the remainder. This process operates most efficiently in young systems when planets are still migrating through protoplanetary disks and can achieve close approaches. Direct collapse involves gravitational fragmentation of molecular clouds regions, where density exceeds the gene's mass. For gravitational instability, collapse into bound objects. Fragmentation at smallest scales produces objects down to several Jupiter masses, if conditions permit. Distinguishing ejected planets from collapsed objects is difficult, requiring detailed spectroscopic analysis of atmospheric compositions, seeking signatures of formation environment. Subsurface oceans might exist on some rogue planets heated by tidal forces or radioactive decay, creating potential habitats for life despite absence of sunlight. Earth mass, or super-Earth rogues with thick hydrogen atmospheres, could maintain liquid water oceans beneath ice layers through greenhouse heating. Hydrogen atmospheres are excellent insulators. High heat capacity and low thermal conductivity trap internal heat. Models show that Earth mass planets with 0.01 to 0.1 Earth mass hydrogen atmospheres could sustain subsurface temperatures above 273 Kelvin for billions of years through primordial heat alone. Adding tidal heating, if the rogue has large moons, creating tidal flexing or radioactive decay from uranium, thorium, and potassium, extends habitability timescales. Jupiter's moon Europa demonstrates tidal heating's power, maintaining a subsurface ocean beneath 15 kilometers of ice, despite receiving minimal sunlight at 5.2 astronomical units from the Sunday. Rogues with similar moons could sustain oceans indefinitely. Without sunlight, photosynthesis becomes impossible, eliminating the energy source supporting most Earth ecosystems. But chemosynthetic life, analogous to Earth's deep-sea hydrothermal vent ecosystems, could theoretically survive using chemical disequilibrium as energy source. On Earth, vent organisms oxidize hydrogen sulfide or methane using dissolved oxygen or sulfate, extracting energy from chemical reactions rather than light. Rogue planet oceans with volcanic activity releasing reduced chemicals like hydrogen, methane, and hydrogen sulfide into water could support similar metabolism. The ocean's oxidized species, perhaps perchlorate or sulfate, would serve as electron acceptors. Life would cluster around volcanic vents or chemical seeps, forming oases in an otherwise barren ocean. Without photosynthetic primary production, biomass would be limited by chemical energy flux from the planet's interior orders of magnitude lower than photosynthesis provides on Earth. But life could persist indefinitely if chemical energy continues flowing, creating isolated biospheres, evolving in absolute darkness, unaware of stars or galaxies. Detecting rogue planets is extraordinarily challenging, except through microlensing or direct imaging at infrared wavelengths. Microlensing requires the rogue to pass almost exactly in front of a background star alignment within micro-arcseconds, making detections rare despite large populations. Direct imaging requires sensitive infrared telescopes detecting the faint thermal glow. Young massive rogues like PSOJ 318, 5-22 are easiest, but cool old rogues like 2 Mass J 1000, 119-1000. 137 push detection limits even for instruments like WISE and Spitzer. Future missions like the James Webb Space Telescope and Nancy Grace Roman Space Telescope will detect cooler rogues through better infrared sensitivity and wide-field surveys. JWST's sensitivity extends to 300 Kelvin objects within 100 light-years, allowing detections of relatively old rogues. Roman's wide-field infrared surveys will discover rogues through both direct imaging and microlensing, potentially characterizing population statistics down to Earth masses and constraining formation mechanisms through mass distributions. The Bootes Void. The Bootes Void, discovered in 1981 by Robert Kirshner and colleagues through galaxy redshift surveys, spans 330 million light-years in diameter, roughly 100 megaparsecs, making it one of the largest known voids in the cosmic web. Centered approximately 700 million light-years from Earth, the void occupies a volume roughly 10 million cubic megaparsecs, containing only 60 galaxies. Comparing this to cosmic average density of roughly 0.1 galaxies per cubic megaparsec, predicts approximately 3,000 galaxies in this volume. The void thus contains only 2% of the expected galaxy population, 98% depleted relative to average. This extreme underdensity defines the void, though even the 60 galaxies present show peculiarities. Many are unusually small and faint, suggesting environmental effects suppressed galaxy formation or evolution in this region. Some border galaxies show blue colors indicating active star formation, possibly triggered by encountering the void's expanding edge. Temperatures throughout the void equal the cosmic microwave backgrounds 2.725 Kelvin, with no significant local heating from stars or active galactic nuclei. The few galaxies present are faint and low mass, producing negligible energy output compared to typical galaxy clusters. Without concentrated matter, gravitational potential wells are shallow, preventing gas from heating through compression. The void's temperature thus remains at the cosmic background temperature, established at recombination 13.8 billion years ago, and redshifted by cosmic expansion. In normal regions, galaxies and clusters heat surrounding gas to millions of Kelvin through gravitational compression and shocks during structure formation. This hot gas emits X-rays and thermal radiation, raising local temperatures above the CMB. In voids, this heating never occurred. The void is the closest approximation to the primordial temperature structure of the early universe, cooled and expanded but otherwise unchanged. Dark energy effects are stronger in underdense regions, accelerating void expansion beyond the cosmic average rate. This phenomenon, predicted by cosmological models including dark energy, results from how cosmic expansion couples to local density. In overdense regions like clusters, gravity slows expansion or causes collapse, creating bound structures decoupled from cosmic expansion. In underdense voids, reduced gravity allows dark energy-driven acceleration to dominate more strongly, expanding voids faster than average. Observations confirm this. Measuring void expansion through peculiar velocities of galaxies surrounding voids shows they recede faster than Hubble flow predicts, indicating voids grow over time. The Boötes void likely formed from an initially slight underdensity, perhaps 10% below average, that grew through gravitational instability in reverse. Matter flowed out of the underdense region towards surrounding overdensities, evacuating the void progressively. The void represents cosmic web structure on the largest scales. The cosmic web consists of filaments, dense threads of galaxies, spanning hundreds of millions of light-years walls, sheets of galaxies surrounding voids and voids themselves. Voids comprise 50 to 70% of the universe's volume, though they contain only 10 to 20% of galaxies. This topology arises naturally from gravitational instability in cold, dark matter models. Overdensities grow through accretion, forming filaments and walls at boundaries between collapsing regions, while underdensities expand and evacuate. Voids are not completely empty. They contain dark matter at densities roughly 20 to 50% of cosmic average, along with the few galaxies that formed from rare high-density fluctuations within the void. The largest voids approach the scales where the universe transitions from inhomogeneous to homogeneous, testing cosmological models predicting the homogeneity scale around 300 to 400 million light-years. Voids comprise 50 to 70% of the universe's volume depending on void definition and survey depth. Defining voids as regions below 50% average density yields volume fractions around 50%. Defining voids as regions below 20% average density yields 30%. The exact fraction depends on redshift, and cosmic epoch voids occupy larger volume fractions at low redshift as they expand while structure collapses elsewhere. Observations using galaxy surveys like SDSS mapped void distributions across billions of light-years, cataloguing thousands of voids ranging from 30 million light-years diameter to over 500 million light-years. Statistical properties, void size distribution, void shapes, void density profiles, constrain cosmological parameters including dark energy equation of state and matter density. Voids are sensitive probes because their evolution depends on gravitational dynamics and dark energy acceleration differently than clusters, providing complementary information to traditional probes. The local void, located between 10 and 100 million light-years from Earth, is a much smaller underdense region adjacent to the local group. With diameter roughly 60 million light-years, the local void partially explains our galaxy's peculiar velocity, the deviation from pure Hubble flow. Matter flows out of the local void towards the Virgo cluster and other surrounding overdensities, producing velocities 200 to 300 kilometers per second. The Milky Way sits on the edge of the local void, experiencing gravitational repulsion more accurately, reduced gravitational attraction compared to opposite directions. Combining the local void's repulsion with Virgo cluster's attraction explains much of the local group's 630 km per second motion relative to the cosmic microwave background rest frame. Mapping the local void through galaxy redshift surveys reveals its structure. Not a smooth sphere, but a complex network of smaller subvoids separated by tenuous filaments containing sparse dwarf galaxies. The potentially larger KBC void, proposed by Ryan Keenan, Amy Barger, and Lennox Cowie, might span 2 billion light-years with Earth near the center. If confirmed, this void would challenge cosmological models predicting maximum void sizes around 300 to 400 million light-years, the homogeneity scale. The KBC void is controversial. Proponents argue that observations show systematic galaxy underdensity extending to 1 billion light-years in all directions, with density below 50% average. Critics contend that better surveys show this apparent underdensity results from incomplete sampling and selection effects, and comprehensive surveys like SDSS find no significant large-scale underdensity. The debate continues. If KBC void exists, it could explain cosmological tensions, including the Hubble constant discrepancy local measurements, yielding higher values than early universe measurements. Living in a large void affects how we interpret observations of cosmic expansion, potentially reconciling different measurements. But most cosmologists remain skeptical, pending definitive confirmation from forthcoming surveys like DESI and Euclid mapping galaxy distributions with unprecedented completeness. The cosmic microwave background cold spot. The CMB cold spot, discovered in WMAP data in 2004 and confirmed by Planck in 2013, spans 10 degrees across the sky, 20 times the Moon's angular diameter, and registers 70 microkelvin colder than the surrounding 2.725 Kelvin cosmic microwave background. This temperature deficit seems small, but in the extremely uniform CMB, where typical fluctuations are only 18 microkelvin, a 70 microkelvin anomaly is enormous. Comprehensive statistical simulations of Gaussian random fields, matching the CMB's power spectrum, find that cold spots this large and this cold occur in fewer than 1-inch 1,000 random realizations. While not reaching 5 sigma certainty levels required for definitive claims, a 1 in 1,000 probability is uncomfortable enough that cosmologists have searched for explanations beyond statistical flukes for 2 decades. The Eridanus supervoid provides a partial but incomplete explanation. Discovered in 2015 by Istvan Shapudi using Pan-STARRS and WISE galaxy surveys, this supervoid sits at redshift Z approximately 0.22, about 2.5 billion light-years away, with a diameter roughly 1.8 billion light-years. Galaxy surveys show the region contains 20 to 30% fewer galaxies than cosmic average, representing significant underdensity, but not the most extreme void known. When CMB photons traverse an underdense region, they experience the integrated Sachs-Wolf effect. Photons fall into the void's gravitational potential well, gaining energy, then climb out, losing energy. If the void grows during photon transit due to dark energy-driven cosmic expansion, photons lose more energy climbing out than they gained falling in, producing a net cooling, a cold spot aligned with the void's position. The ISW effect from Eridanus supervoid predicts only 10 to 20 microkelvin cooling, not the observed 70 microkelvin. Multiple research groups calculated expected temperature decreases using different void density profiles and cosmological parameters. Most estimates fall between 10 and 20 microkelvin, with generous assumptions reaching perhaps 30 microkelvin at most. This leaves 40 to 50 microkelvin unexplained more than half the cold spot's depth. Either the cold spot results from multiple causes, the supervoid, plus a rare primordial cold fluctuation coincidentally aligned in the same direction, or the supervoid is more extreme in dark matter content than galaxy distributions indicate. Neither explanation is satisfying. Coincident alignment of two independent rare phenomena seems contrived, but dark matter being distributed differently than galaxies requires revising galaxy formation models and introducing new physics in structure formation. Multiverse collision hypotheses, proposed by Laura Massini-Houghton in 2007, suggest the cold spot might be a bruise from our universe, colliding with a parallel universe in the eternal inflation multiverse. In eternal inflation models, universes continuously bubble off from inflating spacetime, creating a multiverse of causally disconnected regions. If two bubbles collided early in our universe's history, the collision would leave an imprint as a suppressed region in the CMB, a cold spot lacking normal fluctuations. This idea is highly speculative and essentially untestable. We have no independent evidence for other universes or methods to detect them beyond the cold spot itself. The hypothesis explains one anomaly by invoking a vast framework of parallel universes, which most cosmologists find scientifically unsatisfying, despite its motivation from string theory and inflationary cosmology. Texture defects represent another exotic possibility. Textures are topological defect structures formed during phase transitions in the early universe predicted by some grand unified theories. Unlike cosmic strings or monopoles, textures are non-topological defects that eventually unwind and disappear, but might persist through recombination at 380,000 years. A texture at the surface of last scattering would create a cold region with specific angular size determined by the texture's energy scale. The cold spot's 10-degree size is consistent with gut-scale texture predictions. However, textures produce distinctive polarization patterns in the CMB-specific alignments of electric field directions in photons. Planck's polarization data don't show the expected signatures, weakening the texture explanation. Either textures don't exist, or the cold spot is not a texture, or current polarization sensitivity is insufficient to detect the signals. Discovery by WMAP in 2004 marks the cold spot as one of several CMB anomalies challenging the standard cosmological model. WMAP mapped the entire sky at 5 microwave frequencies with angular resolution 13 arc minutes, detecting temperature fluctuations with microkelvin precision. Statistical analysis identified the cold spot as unusually large and cold compared to model predictions. The WMAP team cautiously noted the anomaly, but emphasized that single universe observations cannot determine whether features are rare fluctuations or indicate new physics. Planck's independent confirmation in 2013, using different instruments and analysis methods, strengthened the case that the cold spot is real, not instrumental artifact. Planck observed at 9 frequencies with higher sensitivity and resolution, improving foreground removal and reducing systematic errors. The cold spot persists in Planck data with essentially identical properties, making it one of the most robust CMB anomalies. Probability calculations for the cold spot vary depending on methodology. Simple Gaussian statistics treating the CMB as a random field with known power spectrum yield probabilities around 0.1 to 1% for a region this cold and this large appearing anywhere on the sky. More sophisticated analyses accounting for look-elsewhere effects searching the entire sky increases chances of finding something unusual somewhere, and non-Gaussian corrections yield similar probabilities. Some researchers argue the cold spot isn't genuinely anomalous when properly accounting for selection effects and multiple testing. Others point out that the cold spot is special not just for being cold, but for being both unusually cold and unusually large. And for aligning with a supervoid, the joint probability of all three properties is lower than coldness alone. The debate continues without consensus, though most agree the cold spot merits continued investigation. The cold spot epitomizes cosmology's current tension between precise observations revealing patterns not perfectly explained by standard models and the lack of conclusive evidence favoring specific alternatives. Lambda CDM cosmology successfully explains the CMB's overall properties, its temperature, fluctuation amplitude, acoustic peaks, to exquisite precision. But detailed examination reveals anomalies. The cold spot, the axis of evil quadrupole, octopole alignment, hemispherical power asymmetry, parity asymmetries. Individually, each has marginal statistical significance around 2 to 3 sigma. Collectively, they suggest the CMB isn't perfectly consistent with simple isotropic Gaussian predictions. Whether these represent genuine deviations requiring new physics or statistical fluctuations that will average out with better data remains unknown. The cold spot is particularly compelling because it's visible. You can see it clearly in temperature maps, making it more tangible than purely statistical anomalies. The Shapley supercluster core. The Shapley supercluster, located 650 million light-years away, contains a mass estimated at 10 to the 16th solar masses, 10 million billion times the Sun's mass, concentrated into a region roughly 100 million light-years across. This makes Shapley the most massive structure in the local universe, within 1 billion light-years. The supercluster comprises more than 25 major galaxy clusters, including Abell 3000, 558, A3000, 562, and A3000, 571, each containing hundreds to thousands of galaxies. The combined gravitational pull from this enormous mass concentration affects the motion of galaxies across hundreds of millions of light-years, including our local group. Shapley's gravitational influence creates a dark flow, a bulk motion of matter toward the supercluster, with velocities reaching 600 to 1,000 kilometers per second, exceeding predictions from standard cosmological models of structure formation. Temperature in Shapley's intracluster gas reaches 100 million Kelvin, measured through X-ray observations detecting thermal Bremsstrahlung emission radiation produced when electrons scatter off ions in hot plasma. At 100 million Kelvin, gas is fully ionized electrons stripped from atoms and emits primarily in the X-ray band at photon energies 1 to 10 kiloelectronvolts. The Chandra X-ray Observatory and XMM Newton have mapped Shapley's X-ray emission, revealing gas distributions throughout the supercluster. The hot gas, heated by gravitational compression during cluster formation and by shocks from mergers, comprises more mass than all visible stars in Shapley's galaxies. Gas mass totals approximately 10 to the 14th solar masses, while stellar mass is roughly 10 to the 13th solar masses. Dark matter dominates with 10 to the 15th solar masses, inferred from gravitational lensing and galaxy velocities. X-ray emission from thermal Bremsstrahlung allows measuring gas temperature and density. The Bremsstrahlung emissivity power, radiated per unit volume, is proportional to electron density squared times temperature to the 1/2 power. Observed X-ray surface brightness combined with known distance yields emissivity, from which temperature and density are derived using spectral fitting. Shapley's central clusters show core temperatures exceeding 10 keV, equivalent to 160 million Kelvin. Cooler regions in cluster outskirts drop to 3 to 5 keV, or 35 to 58 million Kelvin. The temperature distribution maps the gravitational potential. Deeper potential wells compress and heat gas to higher temperatures. The observed temperatures confirm that Shapley contains the predicted dark matter mass required to gravitationally bind such massive clusters. Dark flow toward Shapley suggests additional mass beyond what's visible pulls the local group and surrounding structure. Alexander Kashlinsky and colleagues reported in 2008 measurements of galaxy cluster bulk velocities toward a region near Shapley, with velocities 600 to 1,000 kilometers per second, extending to distances 1 billion light-years. The flow was detected using the kinematic Sunyaev-Zeldovich effect, CMB temperature shifts caused by cluster gas motion. While Shapley's known mass contributes to this flow, calculations suggest it alone cannot fully account for the observed velocities. Either additional mass concentrations exist beyond Shapley in that direction, or mass beyond the observable universe's edge contributes gravitationally exotic dark flow requiring structure outside our cosmic horizon. The dark flow's reality remains controversial. Some analyses find no significant detection, others confirm it, with discrepancies attributable to different analysis methods and systematic error treatment. Gravitational lensing by Shapley's mass distorts images of background galaxies, creating arcs, multiple images, and magnification detectable through deep imaging. Weak lensing subtle shape distortions of background galaxies maps the total mass distribution, including dark matter. Strong lensing dramatic distortions creating giant arcs occurs near cluster cores where surface density is highest. Observations using Hubble Space Telescope and ground-based telescopes with wide-field cameras have detected weak lensing signals from Shapley, confirming mass estimates from X-ray and dynamical methods. The lensing mass matches expectations from galaxy velocities and hot gas distributions, providing consistency checks across independent measurement techniques. Future surveys with Euclid and LSST will measure Shapley's lensing signal with higher precision, potentially revealing substructure in the dark matter distribution. The future fate of Shapley involves continued gravitational collapse as the supercluster's components merge over billions of years. Currently, Shapley's clusters are still falling together, not yet viralized into equilibrium. Over the next 10 to 20 billion years, galaxy clusters within Shapley will merge, forming a single gigantic cluster potentially exceeding 10 to the 16th solar masses. This megacluster will be one of the largest gravitationally bound structures in the universe. Beyond Shapley's boundaries, cosmic expansion driven by dark energy will separate it from distant structures. Regions farther than roughly 5 billion light-years from Shapley are receding faster than light due to cosmic expansion and will never merge with Shapley. The supercluster represents the approximate size of gravitationally bound structures in a dark energy-dominated universe. Larger structures cannot form because expansion wins over gravity. The Sloan Great Wall, discovered in 2003 by J. Richard Gott III and colleagues analyzing Sloan digital sky survey data, extends approximately 1.37 billion light-years in length, making it one of the largest coherent structures ever mapped in the observable universe. The structure appears as a vast filament or sheet of galaxies stretching across a significant fraction of the sky, visible in redshift surveys as a concentration of galaxy positions and velocities, indicating physical association rather than chance alignment. Located at redshift Z, approximately 0.073 to 0.083, corresponding to distances around 1 billion light-years. When light left these galaxies, the Great Wall represents structure formation during an epoch when the universe was roughly 85% its current age. The wall's discovery was enabled by SDSS's systematic spectroscopic survey, measuring redshifts for hundreds of thousands of galaxies, revealing three-dimensional, large-scale structure invisible in two-dimensional sky maps. The Great Wall is a massive filament of galaxies, with estimated total mass around 10 to the 18th solar masses. A quintillion solar masses, or roughly 10,000 times the Milky Way's mass. This mass estimate comes from counting galaxies within the structure and applying mass-to-light ratios derived from galaxy dynamics and gravitational lensing studies. The wall contains thousands of individual galaxies, ranging from dwarf galaxies with billions of solar masses to giant ellipticals exceeding 100 billion solar masses. These galaxies are not uniformly distributed, but cluster into nodes and filaments within the larger wall structure, creating a complex hierarchical pattern. Galaxy clusters, gravitationally bound systems containing hundreds to thousands of galaxies, appear as bright knots embedded in the wall, connected by thinner filaments containing galaxy groups and isolated field galaxies. The entire structure traces the underlying dark matter distribution, which comprises roughly 85% of total mass, while luminous galaxies trace only the visible 15%. Galaxy density along the wall reaches approximately 10 times the cosmic average, creating a vast, overdense, sheet-like structure in the cosmic web. Typical cosmic density is roughly 0.1 galaxies per cubic megaparsec, when averaged over scales exceeding 100 megaparsecs. Within the Sloan Great Wall, densities exceed 1 galaxy per cubic megaparsec in the densest regions. This overdensity is significant but not extreme compared to galaxy clusters, where densities reach 100 to 1,000 times average. The wall's significance lies not in peak density, but in the enormous volume over which moderately elevated density persists. The structure extends hundreds of megaparsecs in 2 dimensions length and width, while remaining relatively thin in the 3rd dimension, only 10 to 20 megaparsecs thick. This sheet-like geometry is characteristic of cosmic web walls, which form at boundaries between expanding voids where matter accumulated during structure formation. The wall challenges lambda CDM cosmology because structures exceeding 1 billion light-years approach the cosmological homogeneity scale, the scale beyond which the universe should appear statistically uniform, with no preferred directions or locations. The cosmological principle, fundamental to standard cosmology, asserts that the universe is homogeneous and isotropic on sufficiently large scales. Observations of the cosmic microwave background confirm this principle on scales exceeding roughly 300 to 400 megaparsecs or 1 billion light-years. Fluctuations in CMB temperature show no correlations beyond this scale, indicating statistical homogeneity. But the Sloan Great Wall, stretching 1.37 billion light-years, appears to violate this expectation. If structures this large exist, the universe might not be homogeneous, even on scales approaching the observable universe's size, challenging foundational cosmological assumptions. Structures this large take longer to form than the universe's age, allows unless initial density fluctuations were larger than observed in the CMB. Structure formation proceeds through gravitational instability. Over-dense regions gravitationally attract surrounding matter, growing denser over time. The growth rate depends on initial fluctuation amplitude and available time. The CMB, showing the universe at 380,000 years old, reveals density fluctuations of only 1 part in 100,000, extremely smooth. Growing these tiny fluctuations into structures with tenfold overdensities requires billions of years. Simulations using lambda CDM cosmology show that billion light-year structures can form, but barely they represent rare high sigma fluctuations occurring in only small fractions of the universe's volume. The Sloan Great Wall appears marginally consistent with predictions, but its existence pushes lambda CDM to its limits. If significantly larger structures exist, or multiple billion light-year structures appear more commonly than expected, lambda CDM would require modification. The Hercules Corona Borealis Great Wall, potentially 10 billion light-years long, represents an even larger challenge to standard cosmology, if confirmed. Reported in 2013 by Istvan Horvath and colleagues based on gamma-ray burst distributions, this structure would be the largest known in the universe, by far more than 7 times longer than the Sloan Great Wall, and approaching the observable universe's 93 billion light-year diameter. The structure appears as a concentration of gamma-ray bursts at redshift Z approximately 2, corresponding to distances around 10 billion light-years. If real, such a structure cannot form through standard gravitational instability within lambda CDM cosmology. There simply hasn't been enough time since the Big Bang for fluctuations to grow this large. The structure's existence is controversial. Critics argue that gamma-ray burst positions might cluster randomly or due to selection effects, rather than tracing real large-scale structure, and that the statistical significance is marginal. The debate surrounding these massive structures highlights tensions in observational cosmology. Lambda CDM successfully explains the CMB, large-scale structure on scales to hundreds of megaparsecs, galaxy formation, and cosmic expansion history. But marginal anomalies persist, structures appearing slightly larger than expected, hemispherical asymmetries in the CMB, tension between local and cosmological measurements of expansion rate. Each anomaly has low statistical significance, individually 2 to 3 sigma, rather than 5 sigma required for confident detection. But collectively, they suggest possible cracks in the standard model. Whether these indicate real physics beyond lambda CDM or reflect statistical flukes and systematic errors remains unresolved. Forthcoming surveys, like DESI mapping 35 million galaxy redshifts and Euclid imaging billions of galaxies, will test structure statistics with unprecedented precision, potentially confirming or refuting these large structures. The Sloan Great Wall's discovery exemplifies the power of large-scale surveys, revealing previously unknown cosmic structure. Before SDSS, galaxy surveys sampled only small patches of sky or shallow depths, missing coherent structures stretching across large volumes. SDSS's systematic coverage, measuring redshifts for galaxies across 10,000 square degrees, 1/4 of the sky, revealed the cosmic web's three-dimensional architecture. Subsequent surveys, including 2 DFGRS and 6 DFGS, confirmed and extended these findings, mapping filaments, walls, and voids throughout the nearby universe. These observations transformed cosmology from theoretical speculation about large-scale structure into empirical science with detailed maps. Modern surveys continue this work, pushing to higher redshifts and fainter galaxies, tracing structure formation across cosmic history from the universe's infancy to today, inside a planetary nebula outflow. NGC 7027, classified as a young planetary nebula located approximately 3,000 light-years away in the constellation Cygnus, displays an outer shell expanding at velocities ranging from 10 to 40 kilometers per second, roughly 20,000 to 90,000 miles per hour. This expansion results from the ejection of the progenitor star's outer envelope during its final evolutionary stages as an asymptotic giant branch star. The shell's temperature varies dramatically with position. The outermost neutral material remains relatively cool at roughly 3,000 Kelvin, similar to a red giant's photosphere, while inner ionized regions heated by the central star's ultraviolet radiation reach 10,000 to 15,000 Kelvin. Observations using radio, infrared, optical, and ultraviolet telescopes reveal complex structure, a bright inner core, multiple shells indicating episodic mass ejection, and jets suggesting bipolar outflow driven by magnetic fields or binary companion interactions. The central white dwarf blazes at a surface temperature of 600,000 Kelvin, more than 100 times hotter than the Sun's surface. This extreme temperature results from the star's exposed core, stripped of its hydrogen envelope and burning helium to carbon and oxygen in a shell surrounding an inert carbon-oxygen core. White dwarfs are extremely compact Earth-sized objects containing solar masses, giving surface gravities 100,000 times Earth's. Their small size produces high surface temperatures through the relationship between luminosity, radius, and temperature. For given luminosity, smaller radius requires higher temperature. NGC 7027's central star has luminosity approximately 10,000 solar luminosities, compressed into a radius smaller than Earth's, yielding its extreme temperature. This makes the star emit most energy as extreme ultraviolet radiation with photon energies 13.6 to 100 electron volts, capable of ionizing hydrogen and heavier elements. The white dwarf's intense UV radiation ionizes the expanding gas, stripping electrons from atoms and creating a plasma glowing with emission lines characteristic of planetary nebulae. Ionization proceeds inside out. Regions nearest the star are fully ionized, while outer regions remain neutral where UV flux drops below ionization threshold. The ionization front the boundary between ionized and neutral gas propagates outward over time as the white dwarf's luminosity increases during its initial post-AGB evolution, then recedes inward as the white dwarf eventually cools and dims. Ionized gas recombines when electrons rejoin atomic nuclei, emitting photons at specific wavelengths determined by quantum mechanics. Hydrogen recombination produces the famous Balmer lines H-alpha at 656 nanometers, giving planetary nebulae their characteristic red color. Forbidden line emission from oxygen, nitrogen, and sulfur transitions, occurring only in low-density gas, where collisional de-excitation is rare, dominates optical spectra, producing green, red, and blue-green colors in images. Mass, totaling 0.1 to 1 solar masses, fills NGC 7027, ejected during the progenitor star's asymptotic giant branch phase over the final 10,000 to 100,000 years before planetary nebula formation. This mass represents the hydrogen envelope surrounding the helium core material originally part of the star's outer layers, but never processed through fusion. Ejection occurs through powerful stellar winds, driven by radiation pressure on dust grains condensing in the cool outer atmosphere. As the AGB star pulsates undergoing thermal pulses, where helium burning temporarily reignites in shells, the envelope becomes loosely bound and easily expelled. Mass loss rates reach 10 to the -4th solar masses per year during super AGB phases, evacuating the envelope over 10,000 to 100,000 years. The ejected material expands into the interstellar medium, enriched with elements created through stellar nucleosynthesis, carbon, nitrogen, oxygen, and trace heavier elements. Radiation pressure and stellar wind from the central star continue accelerating the shell outward even after initial ejection. Radiation pressure acts on dust grains mixed with the gas-solid particles of carbon or silicates with sizes around 0.1 microns, absorb UV photons, and transfer momentum to the gas through collisions. This pressure can exceed gravitational attraction at distances beyond roughly 10,000 astronomical units, where the white dwarf's gravity weakens. Additionally, fast stellar winds hot ionized gas streaming from the white dwarf at velocities 1,000 to 2,000 kilometers per second collide with the slower moving AGB wind, creating shock waves that heat, and accelerate material. The interaction between fast wind and slow AGB wind shapes the nebula's morphology, producing the bipolar and elliptical structures observed in many planetary nebulae, including NGC 7027's elongated form. The environment inside planetary nebulae is hostile to complex chemistry and life. UV flux from the central white dwarf exceeds solar output by factors of 1,000 to 10,000 when considering ionizing photons. This radiation photodissociates molecules, breaking chemical bonds, preventing formation of complex organic compounds. Near the central star, within roughly 1,000 astronomical units, UV flux intensity approaches 10 to the 6th times the solar neighborhood's value, sufficient to destroy any molecular species within seconds. Temperatures range from millions of Kelvin near the white dwarf surface, where coronal gas is heated by X-ray emission, to 10,000 Kelvin in the ionized nebula, and down to 1,000 Kelvin in dense neutral clumps shielded from direct radiation. Gas densities vary by factors exceeding 1 million. From 10 to the 7th particles per cubic centimeter in dense knots, visible as Hubble Space Telescope images bright spots, to 100 particles per cubic centimeter in the diffuse outer halo. These extreme density gradients create complex hydrodynamics. Dense clumps are accelerated more slowly than diffuse gas. Radiation pressure and wind momentum transfer depend on cross-sectional area, but mass determines acceleration, so denser clumps lag behind, creating cometary tails pointing away from the central star. Rayleigh-Taylor instabilities develop where fast wind overtakes slow AGB wind, fragmenting smooth shells into filamentary structures. Thermal instabilities cause gas to condense into cold, dense clumps embedded in hot ionized medium. NGC 7027 shows all these features. Multiple shells indicating episodic ejection, bright knots representing dense clumps, and filaments tracing instability fronts. The nebula's bipolar shape suggests either rotation or magnetic fields, channeling outflows preferentially along polar axes, while denser equatorial material resists acceleration. The nebula fades over 10,000 to 50,000 years as the white dwarf cools and dims, no longer providing sufficient ionizing photons to maintain the nebula's glow. White dwarf cooling follows predictable tracks. Luminosity declines approximately proportional to age to the -7/4 power for young white dwarfs dominated by neutrino cooling, transitating to age to the -1 power for older white dwarfs, cooling through photon emission. As luminosity drops, the ionization front recedes inward, progressively neutralizing the nebula. Recombination timescales at typical nebular densities around 1,000 particles per cubic centimeter are roughly 1,000 years, so the nebula recombines rapidly once ionizing flux declines. Eventually, the nebula disperses completely into the interstellar medium, mixing its enriched material with ambient gas and seeding future star formation with heavy elements. The white dwarf continues cooling over billions of years, eventually becoming a black dwarf, a theoretical stellar remnant, so cool it emits negligible radiation, though the universe is not yet old enough for any black dwarfs to exist. The heat-death endgame. Heat death begins at approximately 10 to the 14th years, 100 trillion years from now, when the last red dwarf stars exhaust their nuclear fuel and fade to black dwarfs, marking the end of the stelliferous era when stars illuminated the cosmos. Red dwarfs, the smallest main sequence stars with masses 0.08 to 0.5 solar masses, burn hydrogen through proton-proton chains at extremely slow rates, giving them lifetimes exceeding the universe's current 13.8 billion year age by factors of 1,000 to 10,000. The smallest red dwarfs, barely massive enough to sustain fusion, will shine for 10 trillion years before depleting their hydrogen. These stars, being fully convective, mix their entire mass continuously, bringing fresh hydrogen to the core and allowing complete fuel consumption impossible in higher mass stars. When the last red dwarf exhausts its hydrogen, around 100 trillion years hence, it will contract and cool, becoming a helium white dwarf, a stellar remnant that never existed before, because the universe was too young for red dwarfs to die. Star formation ceased long before, at approximately 1 trillion years, when galaxies depleted their gas supplies, ending the cycle of stellar birth that characterized the first trillion years of cosmic history. Star formation requires cold, dense molecular gas hydrogen at temperatures below 100 Kelvin, compressed to densities exceeding 100 particles per cubic centimeter. This gas exists in giant molecular clouds within galaxy disks, regions where gravity overcomes thermal pressure, allowing gravitational collapse into stars. But star formation and stellar feedback supernovae, stellar winds, AGN activity gradually deplete and heat galactic gas reservoirs. Supernovae inject energy into the interstellar medium, heating gas to millions of Kelvin and launching it into intergalactic space as galactic winds. Over billions of years, gas reservoirs deplete faster than replenishment from the intergalactic medium, which itself becomes ionized and dispersed. By roughly 1 trillion years, essentially all cold gas has converted to stars or been expelled, terminating star formation. The final stars form from the last scraps of molecular material, producing a final generation of low-mass stars that will burn for trillions of years. The degenerate era follows, with the universe populated solely by stellar remnants. White dwarfs comprising approximately 97% of all stellar remnants, neutron stars from massive star supernovae making up roughly 2%, and stellar mass black holes from the most massive stars constituting the remaining 1%. White dwarfs are Earth-sized objects containing 0.5 to 1.4 solar masses, supported against gravitational collapse by electron degeneracy pressure, quantum mechanical pressure, arising from the Pauli exclusion principle, preventing multiple electrons from occupying identical quantum states. These objects cool slowly through thermal radiation, their temperatures declining from initial values around 100,000 Kelvin to 10,000 Kelvin over their first billion years, then to 5,000 Kelvin over 10 billion years. Cooling rate decreases as temperature drops because radiative losses scale as temperature to the fourth power. By 100 trillion years, white dwarfs have cooled to roughly 5 Kelvin, barely above the cosmic microwave background temperature, which by then has cooled to approximately 0.3 Kelvin due to cosmic expansion's redshifting effect. Galaxy evaporation through gravitational scattering occurs over timescales 10 to the 19th to 10 to the 20th years, 10 billion trillion to 100 billion trillion years, as stellar encounters randomly exchange energy, occasionally accelerating stars above escape velocity. This process resembles planetary evaporation from solar systems, but operates on galactic scales. In gravitationally bound systems like galaxies, stars orbit the galactic center, following elliptical trajectories. Close encounters between stars occurring when two stars pass within roughly 1 light-year exchange orbital energy and angular momentum. Most encounters are gentle, slightly altering velocities, but rare close encounters can accelerate one star to velocities exceeding the galaxy's escape velocity, roughly 500 kilometers per second for Milky Way-sized galaxies. The ejected star escapes into intergalactic space, carrying away orbital energy and causing the remaining system to contract slightly. Over time, repeated ejections evaporate roughly half the galaxy's stellar mass, while the other half collapses inward, ultimately accreting onto the central supermassive black hole. Black holes dominate the black hole era, spanning approximately 10 to the 40th to 10 to the 100th years, slowly evaporating through Hawking radiation, quantum radiation, emitted from black hole event horizons, through vacuum fluctuations. Hawking radiation arises from quantum field theory in curved spacetime. Virtual particle-antiparticle pairs produced near the event horizon occasionally have one partner fall into the black hole while the other escapes, appearing as thermal radiation to distant observers. The radiation temperature is inversely proportional to black hole mass. T equals h bar c cubed divided by 8 pi gm k Boltzmann. For stellar mass black holes around 10 solar masses, temperature is roughly 6 billionths of a Kelvin, far colder than the cosmic microwave background. These black holes currently gain mass from CMB accretion faster than they lose it through Hawking evaporation. But as the universe expands and CMB cools, eventually Hawking evaporation dominates. Stellar black holes evaporate in approximately 10 to the 67th years. Supermassive black holes take vastly longer. The Milky Way's 4 million solar mass black hole evaporates in roughly 10 to the 87th years, while the most massive billion solar mass black holes survive until 10 to the 100th years. Proton decay, if it occurs as grand unified theories predict, dissolves all atomic matter by approximately 10 to the 36th years, leaving only radiation, leptons, and black holes as the universe's constituents. The standard model of particle physics assumes protons are absolutely stable with infinite lifetime. But grand unified theories unifying electromagnetic, weak, and strong forces predict protons decay through processes violating baryon number conservation, with lifetimes around 10 to the 34th to 10 to the 36th years. Decay products include positrons, neutrinos, pions, and photons, depending on decay channel. If proton decay occurs, all atomic nuclei eventually disintegrate. White dwarfs, composed of carbon and oxygen nuclei, dissolve into clouds of positrons, electrons, neutrinos, and photons. Neutron stars similarly decay if protons within neutrons are accessible, though quantum chromodynamics effects in superdense matter might alter decay rates. Experiments searching for proton decay in underground detectors like Supercameo-Candy have not observed it despite sensitivities reaching 10 to the 34th year lifetimes, suggesting either protons are truly stable or decay timescales exceed experimental limits. Final temperature asymptotically approaches 10 to the minus 30th Kelvin, effectively absolute zero, as the universe reaches maximum entropy with no usable energy remaining for work. Temperature continues declining as cosmic expansion redshifts, all radiation photons from white dwarf cooling, Hawking radiation from evaporating black holes, and the cosmic microwave background itself. The relationship between scale factor and temperature is T proportional to A to the minus first power, where A is the cosmic scale factor growing exponentially under dark energy domination. As A increases without bound, temperature decreases towards zero. Entropy increases continuously as all ordered energy stellar radiation, black hole mass, particle rest mass degrades into uniform background radiation. Maximum entropy corresponds to thermal equilibrium at uniform temperature across all space, with no gradients permitting energy flow or work extraction. This is heat death, a universe in thermodynamic equilibrium, dark, cold, and unchanging for eternity. Boltzmann brains's random quantum fluctuations temporarily creating conscious entities might be the only structures arising in the far future's featureless thermal bath, though their probability is vanishingly small across any finite timescale. In thermal equilibrium, quantum fluctuations still occur through the uncertainty principle, allowing temporary violations of energy conservation, creating particle-antiparticle pairs, or even complex structures. Given infinite time, any finite probability event eventually occurs, including fluctuations assembling configurations, mimicking conscious observers' Boltzmann brains. These entities would exist briefly, experiencing one conscious moment before dissipating back into random fluctuations. The probability of fluctuating into a minimal Boltzmann brain is enormously higher than fluctuating into an entire universe or civilization, leading to the Boltzmann brain paradox. In cosmologies persisting infinitely, random brains vastly outnumber evolved observers, making our existence as evolved beings puzzling. Resolving this paradox might require reconsidering assumptions about cosmology's far future, quantum mechanics in infinite time, or consciousness itself,